About the Weald Basin, and hopefully you'll enjoy listening to me talk about it because it's actually quite a fascinating story. And it's one of these stories I like because it's kind of got a beginning, a middle, and hopefully a quite happy ending on this one, which is developing as we speak. So if we just bring on the next slide. So, was there anything projecting? It will in a second. Oh, look at that. As if by magic, we're in business. So this was originally a 45-minute talk. I will talk about the geological setting. The exploration history is the interesting bit, because that's the story in this, in that we started, a bunch of BP geologists came back from, so I have to stand in front of the podium, came back from the Middle East in the 30s. And they were been very successful drilling big anticlines with carbonate reservoirs. This is in what used to be called Persia. It's actually present-day Iran, with great success. And they'd had 30 years of success on the flanks of the Persian Gulf drilling these. And they came back to Britain and said, well, new petroleum law in 1934, we can do the same here. And so they looked around the UK, and you'll probably be aware they drilled a few early wells up in Scotland and a few around the Midlands, but they saw these great big anticlines at the surface in southern England. So they thought they'd have a go at these. So we'll talk a little bit about how they tried to export, really play fairway analysis from the Middle East to southern England, largely without success. And then, of course, we all know which farm was eventually discovered in this unsuccessful basin, which I think gives all of us as explorers hope that if you keep looking with new ideas and new technology, you can finally get successful. But it was only one real success at which farm. So we'll go on to talk about what's happened recently. And I was exploration manager for BP for Southern England, and I missed this. I drilled the Brocken well and missed it. There is a new play which has emerged over the last few years, which I think has really opened up the Weald Basin as a new, potentially quite large oil province, but more importantly, it's giving us an answer to why wonderful source rocks in the Weald Basin never really gave us a wonderful petroleum province. So that's going to be the story. Where are we? So this is, I'm sorry, the coastline of England is not quite as bright as it should be in this blue colour, but we're here at the Geological here. The Weald Basin is directly south of us, and the Portland South White Basin, the Wessex Basin, is offset to the south of that by about 50 or 60 kilometres. So there's two basins we're looking at. The geology, the stratigraphy, and the tectonics are very similar. In terms of stratigraphy and the key intervals I want you to kind of know about, down here we've got a source rock in the lias. That's very important in the Wessex Basin. It's almost certainly the main source rock for the Witch Farm oil field, and it's deep in the Jurassic, and it's generally mature to early gas mature in the Wessex Basin. The Oxford clay, another world-class source rock, often not quite as mature as the lias, but sits up there in the latest part of the middle Jurassic to the upper Jurassic, and then finally the Kimmeridge clay of North Sea fame. Now, I kind of wrote the Kimmeridge clay off when I originally looked at the Weald and Wessex Basin, and because I said it was immature, and published on that, by the way, and found out this was totally wrong. But I'm prepared to accept my mistake in this case, because we all learn as we work. The basins are formed on the collapse of Variscan thrusts. So these are late Carboniferous thrusts that were present throughout northern France, Belgium, England, South Wales, and offshore Southern Ireland. And the basins actually collapsed on these thrusts, so that these are the Mesozoic basins of the Celtic Sea. The Weald and Wessex are exactly similar. So because the Variscan fabric was very much west-east, we got a very strong west-east fabric to the Weald and Wessex basins. And when it came to actually the alpine compression in the tertiary, the Variscan orogeny was reactivated in a compressional sense, and these basins became inverted basins. Again, I've got quite a lot of geology in here, which we won't have time in this talk to talk about, but we start with rifting in the Triassic. It's north-south, so it actually cut across the Variscan orogeny was quite different. The important thing about this was there was a large salt basin off the Dorset coast at that time, and there's some wonderful outcrops. This is the lias, so there's two main deeper centres, the Weald, up to about 800 metres, and the Portland South White, up to about 1,000 metres of lias. Now, given most of that is black shale interbedded with thin micritic carbonates, that is quite a high net to gross, fairly rich source rock. And that has, in here, provided the main source for Witch Farm. Up here, it's not as rich. It's much leaner, and if anything, it's only managed to produce a little bit of gas for us in the Weald Basin. This is the Middle Jurassic, very different. Rifting had stopped, and we had a broad carbonate shelf. Now, the reason I'm showing you the Middle Jurassic, because it's a direct analogy to what's happening in the Upper Jurassic with these micritic carbonates I'll show you later. This is the Weald sequence, the Lower Cretaceous. This is key. This is what matured the source rocks. So, in fact, this is kind of the treasure map. If you know where your source rocks were matured here and here, you can pretty much find all the conventional oil that's present in the basin. It also is going to help us with the unconventional oil, the shale. Where was the shale mature? Where is it still containing oil and gas? And then finally, the tertiary, after the alpine inversion, very different. All the deposition was on the original footwalls to these big faults. So we've shifted and inverted the depositional pattern. The only impact this really has had on the petroleum system is these areas here and here have been largely undeformed by the alpine orogeny. And that becomes important when you're looking for oil in fault blocks. Right, here's the history. Here's the early BP explorers in Iran. Classic 3 men, 2 dogs, and quite a few bottles of claret. Clearly, this was lunchtime. And what they were doing was a classic form of early play fairway analysis. They were mapping surface anticlines, and they were walking the streams where the water table came to near surface and logging the seeps. And when they got a seep and an anticline coinciding, that's where they drilled. And that's how the first discoveries in Iran and Iraq were actually made. Majidi Suleiman was the first one. So that's over a century ago. So here we go, back to the Wessex Basin. This is a quarter scene thematic mapper Landsat. To reference ourselves, these red areas are the towns of Poole and Bournemouth. This is the New Forest, this is the chalk, this is essentially the Jurassic clays up here at Outcrop. But along here we can see beautifully picked out is the Weymouth anticline. So you can see these features are observable at surface and also from space. We've also got seeps at some locations, live seeps today along the coast. So let's have a look at the evidence. Here's what the anticlines look like. There's that salt I mentioned, actually helping form these anticlines. It's a beautiful anticline, the Weymouth anticline. And it has been drilled at least 4 times, all without success. But it has been drilled, but why not drill that? The surface geology picks the anticline out perfectly as well. So you didn't need seismic to find this guy. This is what you see at the surface. This is what we do with students on the field trip. This is Moot Bay. That's fairly live oil in the Lower Cretaceous, the Wealden. Here is with Oswington Mills. So this is the Corallian. So again, live oil. And at the right tide levels, you actually see the oil bubbling up in the foreshore. So it's still coming out through the fault systems. So all the right signs. We've got oil, we've got carbonates. What could possibly go wrong? Well, let's have a look at the structure. I've got a couple of lines to show you across the Weald Basin. So that's the eastern basin here. So again, London's up here. So this is the Weald anticline here. And these are some of the early efforts. This was called stagecoach geology because they didn't use minibuses and coaches in these days. They used stagecoaches. And every time the stagecoach stopped to water the horses, they go out and did the geology. And this attempt by John Farry, 1807, guys, that's pretty good. When I show you the seismic, that's just about nailed what the Weald Basin anticlinorium looks like. Despite his much heralded expertise in stratigraphy, structure wasn't one of William Smith's strong points. So we've got this sort of strange trapdoor effect, and you'll see that this isn't actually quite right. But given the time, and the way it was mapped, no problem. Just keep me right on time, will you, Adrian? Right, here's the seismic. This is easy, isn't it? We've got the benefit of modern technology to see that Farry's attempt at the Weald was pretty good. And so there's the South Downs, there's the North Downs, and there's the soft fluvial and lacustrine sediments of the lower Cretaceous Weald eroded away in the middle. So there's our basin. So what it looks like, the source rocks and the lias are down here, the Oxford clay here, and this bright amplitude, which everybody likes mapping, was actually the Kimmeridge and the Kimmeridge carbonate. But we kind of ignored it. It's just a tight micrite, never produced from that. So this is how the basin formed. There's the Triassic rifting, and then we put the lias on top, and that big blue sequence is the Kimmeridge. And then the thick oranges and browns, that's the early Cretaceous, so that's a rift sequence. Now we put the chalk on. Now something nasty is going to happen, and that's the alpine orogeny. So it formed probably a 2 to 2.5 kilometre high mountain. But the chalk eventually eroded back about 30 million years ago, and it cut very quickly down into the Weald. So we've got the present-day basin configuration. But the important thing about that diagram is 30 million years ago, this basin was at maximum burial. All these source rocks were mature. The lias, the Oxford clay, and the Kimmeridge, more importantly. So we can work the petroleum system using this. Let's go back to the first well that was really drilled in the Weald Basin in Anglia. This is the Sub-Wealden Exploration Company's well at Netherfield. You'll notice there are no protesters on this well. Clearly, the concept of fracking hadn't really got through to the general public at this time, nor the rig safety. But the key thing is, and it's reported beautifully in the proceedings of the Sub-Wealden Exploration Company, they went down to the cores from the Kimmeridge. The cores were landed, these are full cores, and they noted oil bleeding from the carbonate rocks. Now, it's just a record in an old report. There's no record of where the cores are or any core description. Just the oil was bleeding from probably the oldest stratigraphy on the Weald Basin. It was actually drilled to try and find out what was below the Cretaceous and the Weald. So this well that's miraculously sunk was the first well drilled by BP. This was the Portsdown well in Hampshire. So it was on the Portsdown anticline. And to cut a long story short, that one really didn't work. It got down to the Triassic, 2,000 metres, but the anticline didn't work. Despite all these source rocks, all these seeps, no oil. The only discovery made in an anticline in southern England was at Kimmeridge Bay. And this confused me for years when I was at BP. So I came up with this wild story. I mapped it, 2 million barrels. It's produced over 2 million barrels. There has to be recharged this, and I came up with this wild story. It was being recharged into the Cornbrash, the Middle Jurassic Reservoir, from the footwall. Well, that's nonsense. Wrong. What we actually have in Kimmeridge is something that we're beginning to find is starting to work elsewhere in the Weald. It's a hybrid play. The limestone is naturally fractured. The Oxford clay is mature. There was my horrible map. Sorry, I'll just show you. There's the students at the Nodding Donkey, which is still producing 60 barrels a day. Right, that's a better diagram of what it looks like. So there's the anticline. The oil is in the Cornbrash, in the very fractured Cornbrash in this tight anticline. Here's the basin model for Kimmeridge. And the key thing is, here's our Jurassic. And the Oxford clay is the key, and the Oxford clay here is in the oil window. The Kimmeridge is very early oil, but the Oxford is mature. So the Kimmeridge at the surface in Kimmeridge Bay is just about mature. The Oxford is mature. This is key. So as the fractures were formed in that well, I believe now that the Oxford clay actually exsolved and produced its oil into these fractures as they formed. And we've been looking at these fractures recently with one of my students, Francesco, who's in the audience, and we're actually seeing that they fit very nicely with this story. So the whole Weald Basin changed. We'd all walked away from it. I was taken out of UK land. A lot of it was sold by BP, and I was sent to Houston to go and find some oil in the Gulf of Mexico. Until this happened in 2014. And very close to where I had been drilling wells in the Weald, UKOG, United Kingdom Oil and Gas, actually produced up to about 1,000 barrels a day from fractured Kimmeridge limestones. Now, there was all sorts of hype at the time about reserves in the basin that were emphatically and clearly wrong. But the important thing about this well, the Kimmeridge was mature, and it produced oil. Now, breaking news. The Kimmeridge limestone, yesterday, Angus Energy, Volcom 2Z, they conducted a 7-day test, and they announced yesterday that again from these Kimmeridge limestones, over 1,500 barrels of oil a day. And that was a 7-day test. A little bit of water, which was still to explain, but lovely oil from naturally fractured Kimmeridge micrite. So that's another success. At Horse Hill, now we've got Volcom 2Z. This seems to be working. It's quite scary. So these are the source rocks we've talked about. I don't want to spend too much time going through them. They are all world class. The Wheel Basin really has, and the Wessex Basin contains excellent source rocks. We've analysed them. The TRCs of some of these are phenomenal. The Kimmeridge clay right up to sort of beyond 12%, up to 20%. Oxford clay, the lower part of the Oxford clay is an excellent shale and is probably producing a lot of the oil we're seeing in the basin. They're not really shales that are going to frack. So you're going to need the limestone. So they're all sitting down, they're all sitting down in the clay end of the diagram. So we've modelled these. Francesco's modelled them, another one of my students has modelled them. And the thing we're finding out is that the source rocks are mature. They are charging the limestones, they're charging the conventional fields. The thing we got wrong was we used the wrong kinetics. And I'm beginning to learn it's not just heat flow, burial, uplift that's key to working out a shale play. You have to understand the kinetics of the shale. And if you use kinetics from the North Sea Kimmeridge clay, you get this wrong. This is a much more rich Kimmeridge clay, in certain parts, much richer than the Kimmeridge clay the North Sea ever gets to. So that has been key. Well, we've added a bit of burial as well, Francesco, which has helped. But using the basin modelling tool, Petromod, we've actually been able to recreate most of the conventional oil fields in the basin and predict the future unconventionals. So we've done a lot of geochemistry. Again, I'm not going to go into too much detail on it. The story is that this is when the basin was a world-class petroleum system. This is when the world-class petroleum system, present day, or from about 30 million years, was completely and utterly disrupted. So where was the missing oil was the question. And I think we've actually started to find it in the micrites. And these are what they look like. They're a series of shoaling carbonates that by the time you get to the Wessex Basin are deep water, or fairly deep water relatively, 50 to 100 metres of water, but are very shallow water in the Wheel Basin. So we're seeing these progradational sets of micritic carbonates coming out in the basin. And we can see them in the XRD and the mineralogy as well, carbonates improving. And the key to it working is the natural fractures. And we're still working on this, but what seems to be happening is as the basin has been uplifted, as it's been eroded, the pressure change within the Kimmeridge source rock and the limestones has induced natural fracturing, natural hydraulic fracturing within the limestones. You've created this porosity and permeability. The source rocks are mature but overpressured, and they've just gone straight into the limestone. And when I did this talk before, I describe it as a sort of Oreo cookie plane. You've got the shales with the limestones, and there's 4 of them actually interbedded with them. So I think that's how it's working. Just to summarise, I don't know how the time's going, Adrian, are we okay?
Yeah, you're fine.
Started off by a bunch of BP explorers from the Middle East deciding they wanted to drill anticlines and carbonates. It patently didn't work. And it didn't work because they got the timing wrong. In the Middle East, the oil charge came after the anticlines were formed. In the Weald, it came before the anticlines were formed. In the Weald, it came after the anticlines were formed. A major timing issue. The reason Kimmeridge is an anticline works because it's not a conventional play. It's been charged, probably still today, by the mature interbedded Oxford clay. I didn't talk much about the Witch Farm discovery, but the key there was it was sitting in that undisturbed part of the Wessex Basin where the tertiary is thick, the New Forest. And therefore it wasn't moved, it wasn't inverted. So the oil that got into Witch Farm during the late Cretaceous and early Tertiary just stayed there. There's been a bit of tilt. Probably about a third of the reserves have migrated to the west, where they're found at Warwick's Cross and Wareham Stillborough and Army Point. But the basin has got new life because shale has given it a new life. The source rocks were always there. They were always mature. I might not have realized they were always mature, but I do now. And modern techniques of looking for hybrid plays, understanding shales, has actually shown that the centre of the Wheel Basin might actually turn into quite a significant oil province, particularly if these fractured, naturally fractured limestones continue to work. Okay, thank you very much. That's the story of the Wheel Basin. Sorry, that was a bit of a race.
Does anybody have any questions for Al related to the talk directly? Just let me check my glasses for time.
There's one at the back. Yes. Oh, I think you're going to get a microphone.
Yeah.
But we won't ask you to say.
I'm tone deaf. You definitely don't want me to say. Hi, Dr. Joanna Forwalker, UCL. You mentioned that the importance of the role of the clays just now towards the end with the inversion, and you had the clays coming in. I was just wondering if you could sort of say a bit more about those clays and the impact they're having there.
What the clays within, as they're uplifted?
Yes, exactly.
What seems to be happening, there's two things happen. One, the clays are getting overpressured because once they're uplifted and eroded, they're at a normal pressure for the depth. The only place that pressure can go is upwards. But that would take quite a while. But if you're creating natural fractures in the limestones that are interbedded with them, I think the clays just, all this oil that's been trapped within the Kimmeridge and the Oxford clay, which is right below it, is going into the limestone. My prediction was there'd be no water in this system. I'm not sure if that's correct yet, because you're forming the fractures, the clays are saturated with oil and just desperate to get rid of it. And then you create this porosity and permeability, and I think that's how they lose their pressure. And so it happens, I think, quite rapidly. There's nowhere for water to come from. The fractures and the porosities formed, the only thing that goes into is oil. So I think it's going to be pretty much an oil-wet system, but still work to do. The petrophysics can't handle this play at the moment, so we've got some new technology to develop before we can learn about it. Thank you. They'll get you the microphone.
Thank you. Alberto Guadagnini from the Politecnico di Milano. You were mentioning kinetics and the importance of having the right kinetics. Can you say something more about the way you estimated parameters of those kinetics, whether they are certain, if they have some uncertainty associated with them, if it is a big, small uncertainty?
The benefit of modern pyrolysis techniques to working out the kinetics of a particular source rock is immense. We've been using the HAWK tool based in Utah University, University of Utah in Salt Lake City. So the data has come from the scientists there. But it's clearly showing that, and not just in the Weald, but in East Midlands and Northern England, we're seeing both the shales here and the Bowling shales quite differently. And I think we got up to, I think, 14-point kinetics, Francesco, is what we put into them. So we're actually saying primary oil production, gas production, and secondary gas kinetics. It really is, it's made a lot of difference to the primitive stuff we did back in the 90s.
Thank you.
Yes. But we can stop if you want.
No. This is perfect.
Just raise the hand before I have two mics so I can...
Oh, right.
So, John Shaw, University of Alberta, just a quick question about the nature of the oil that you perceive as present, and then in a production plan, would it have a high density of wells, or is this oil a heavy oil, or something about the fluids themselves?
Right. The oil from the test reported yesterday was 36 to 40 API. That's consistent with what other people have published. It is from a type 2 kerogen, we know that. What's very difficult to tell is whether it's from the Kimmeridge or the Oxford clay, they are geologically fairly similar. So it's going to take some sophisticated geochemistry to sort them out. But I suspect there's a mix. Since both source rocks are mature, they will naturally mix by vertical migration within the reservoir. Production. I think that's quite a bit away. We are limited in the UK with the number of sites, wells, we're going to be able to put in. There's quite a lot of, as you'll hear probably later today, opposition to fracking. The great thing here is you're not allowed, you can't frack this stuff because it's too shallow, and two, you don't need to because it seems to be quite densely naturally fractured. So it's just a matter of, given it's shallow, can you get the horizontal wells in? Which direction do you put the horizontal wells to maximize production? And we'll see where we go. But you've got to remember, this is, fairly, south of London is commuter belt, rich, highly educated people who are quite capable of motivating themselves to stop oil operations.
It's also a beautiful walking area.
It is, but I always say Scotland's a lot nicer, but there's no, but there's no shale oil and gas up there. But yes, it's going to be a problem, so you have to minimise it. But the resource is beginning to look like it's there. So it was a complete surprise to me, by the way. I never saw this coming, so I've learnt a lot. But no, I don't know how the production will go ahead, but it sounds as if the resource on a regional, semi-regional scale is proving up. That Balkan well was in a very nice place for this to work.
Another round of applause.
Ah, thank you.
Very much.
You're most welcome. That's yours, I think.
And will you be around for the rest of the day? Are you able to?
Yeah, the rest tomorrow.
Perfect. So if there are more questions for Al, please catch him at coffee or in a later part of the session. Okay, we're a little bit ahead of schedule, but I think I'd like to run it that way, and then we can have a little bit more time later on. I'd like to now introduce Alberto Striolo, my colleague from University College London, who's going to give us an overview of the ShaleXenvironmenT project, which we've been working on just the last 2 days. Well, for 3 years plus the last 2 days.
Thank you, Adrian. I would like to start by thanking Adrian and Eugenia for putting this forum together. It's a pleasure to be here, of course. And I would really like to thank all of you for joining us, because today is a celebration. We celebrate the successful completion of 3 years of activities in the ShaleXenvironmenT consortium. For this celebration, you've seen that we have invited people from across the whole world. What we would like to do is to share with you what we have done and to see what is that is being happening in other consortia, other industries, other groups that have conducted similar work across the world. And the whole point is to try to make research and the technology as good as we can. And you can see from the agenda over here that we put together technical presentations, industrial presentations, academic presentations, but also presentations that have a formal acknowledgement of the importance of social sciences and also an importance to the legal aspects for the process of attempting to produce shale gas. So I think it's a great day, and let's see what happens today. My job here is to try to give you an overview of what the ShaleXenvironmenT consortium has been working on for the past 3 years. It's impossible to give justice to everybody that has done a significant amount of work over this length of time. So what we have decided to do is to ask as many people as possible to give posters presentations. So those posters are available on the back, and those are the people that have conducted the work. So the real good questions, the important stuff, those are the people who know the results. My role is essentially just to give you an overview and to try to give justice to these activities that people have conducted. So the title of this consortium is ShaleXenvironmenT, in case you haven't read it yet, and we have been running this for the past 3 years. So when we started these activities, these were the reasons why we decided to study shale gas. Let's start from the bottom left, why not? That is a plot that shows the CO2 emissions from the US as a function of time. And what you noticed here is that around 2005, there is a decrease in these emissions. Part of that decrease was due to economic problems in the country, but part of those decrease in emissions was due to the fact that a number of energy plants were shifted from coal to natural gas. So using natural gas instead of coal has the potential of reducing the CO2 emissions. Down here is another reason why we decided to study shale gas. This is a pamphlet that produced by people that work in Washington to steer the political agenda. And what that pamphlet summarizes is the number of jobs that were created in the US as a consequence of the shale gas revolution. Those numbers are quite impressive. And remember, we put together this proposal in 2013, and in Europe, the high cost of natural gas was encouraging some companies to shift production from Europe to other places in the world. Up there, I show a relatively old map that shows the shale gas formations across Europe. If you look at similar maps across the world, what you will notice is that shale gas formations are pretty much ubiquitous. They tend to be pretty much everywhere, and especially in places where traditional oil and gas is not found. So that idea suggests that perhaps if we learn how to produce shale gas in a way that is environmentally conscious, we might be able to achieve energy independence. Up here is a more recent plot. It's from last year. It's produced by the International Energy Agency, and that is the projection until 2040 for the primary energy demand. Those little balls represent changes in energy demand. The yellow ones are increased energy demand, and the red ones are decreased energy demands. So you see that the old regions of the world, Europe and the US, are expected to have somewhat of a decrease in energy demand, but a lot of new regions in the world are going to have a lot of increased amount of energy demand. Many forms of energy are going to contribute to this. Perhaps, most likely, natural gas is going to be one of the forms of energy that is going to contribute. So those were the reasons why we thought that natural gas could be useful. And that justified our interest in studying natural gas and how it can be produced. Now, of course, there are associated risks. And these should not be underestimated. I'm an engineer, so let's start by an economic point of view. Up there on the left, those are the number of wells that were drilled in Poland as a function of time in the recent past. And what you can see is that those number increased and then it decreased. It decreased because it was simply not economical to produce shale gas in the Poland formations. Each one of the shale gas well can be anywhere between 1 and 10 millions. The industrial speakers later on can give us a better estimate for those costs. But there we have maybe 25 wells at some point. That's 250 million investment that led nowhere. So just from the economic point of view, it's important to know what you're doing. Perhaps more importantly, in this graph over here that I stole from one of the other shale gas projects that were funded by the European Commission, there are a number of environmental risks that are associated with producing hydrocarbons. We will hear more about what other projects have done to try to limit these risks, but risks that are commonly associated in the public opinion with natural gas production include induced seismicity, gaseous emissions, and possible effects to the drinking water. Those are just some of the possible risks. It's possible to list all the possible risks, and it is also possible to try to limit the aftermath of such risks. If the industry, the academia, does not address these issues, what we have is the outcome of a public response. This is a picture that was taken in the UK. Al was referring to these relatively frequent outbursts, and these are well understood. These are very highly populated areas. people know what's happening, and if we don't address what is in their minds, they may simply not want the production of natural gas in their neighborhoods. All right? So these are all, well, some of the possible risks that are connected to the production of shale gas. Perhaps a description of SXT is a fundamental research-focused attempt to limit these risks. So the way that I put it there is environmental impact mitigation via fundamental research. All our activities are devoted to try to understand the asset, try to minimize the environmental impact, and try to innovate the technology. We put together a consortium. The partners are over there. The partners are across the entire Europe. We have academia, we have small and medium enterprises, and we have large industrial partners. And the idea that we put in there was that if we want to do this environmental assessment, we need to do it on a place-by-place approach. So the original workflow that we came up with was, okay, let's work on a single well. If we want to understand the asset, we need to have access to the core rock samples. Then we need to characterize them. And perhaps the traditional techniques were not useful for characterizing the rock samples. Then we need to understand the fluid behavior. The pores in shales are very different compared to the pores in conventional rocks. So perhaps the fluids behave differently. Once we have this understanding, we should try to estimate the production of a well. And we just learned that that activity is not such easy. Science keeps changing, and our ability to estimate the possible production from a formation changes as time progresses and as the technology progresses. Then, of course, we got to be transparent. We need to estimate these risks and the possible consequences. And as mentioned briefly, the risks are real, and we need to be able to do something about them. Then perhaps what was a little bit the unique approach of the SXT consortium was to propose to estimate this worthiness factor W. Essentially, the idea here is that we need to compare the risks and the benefits. If in a formation the risks are too high, that formation perhaps should not be produced. If, on the other hand, the risks are manageable and the expected productivity is very large, perhaps that formation should be considered for production. But that discussion should not be based only in academia or in industry. That discussion should include all stakeholders. And of course, we are not the experts for that discussion to be happening. We can only provide some information for that discussion to be informed. That was the job that the SXT decided to try to accomplish. This presentation was used yesterday to figure out what was the success of the SXT consortium. And this is what I think is the impact summary of our activities over the past 3 years. So when we put together this proposal, we said, okay, we should be able to minimize the environmental footprint. 3 years later, did we succeed or not? Those WP are meant to be work packages, and we had 12 work packages, 10 of which were scientific. No, 9 of which were scientific. Those 9 work packages will have posters on the back for you to try to figure out the details of those activities. But work package 8 identified solutions to treat the water in a way that was both economical, socially acceptable, and that was also minimizing the environmental impact. Work package 9 detailed the possibilities of seismic events, and they did an analysis across the world in many human-based activities. Work package 6 developed some software that is able to see the changes in the pressure in the subsurface as a consequence of the stimulation of the formations. And using that, one can try to estimate the possibilities of induced seismicity. Work package 9 also looked at the possibility of a well to blow out, and what are the strategies that can be implemented to limit the consequences of such unlikely scenario, but it does happen from time to time. Work package 10 quantified and compared the possible emissions between shale gas and many other forms of energies, and they used a life cycle assessment to do that. So that now we can compare, for example, coal, natural gas, or nuclear energy in terms of as close as possible comparisons. We wanted to innovate the technology. What did we do? Well, Work Package 2, in collaboration between UCL and Halliburton, was able to improve the handling of the core samples at conditions that are as close as possible to the subsurface. Work is not complete, but we are on the right track. Work Package 3, this is works predominantly from Potsdam and from the University of Manchester. They innovated the way we can look at these core samples and understand the properties that they have. Some of these innovations that I'm listing now, they are cutting edge. We are the only people, well, people in the consortium are the only people in the world that are able to do this. Work Package 3 is one of them. Work Package 4, they identify new ways in which it is possible to stimulate those shale formations. This work package is led by Andrei on the back, and we have contributions from the Czech Republic, from Greece, and a little bit from London. Work Package 5 from Florence, they innovated the formulations that are used as fracturing fluids. They came up with ways to make these formulations completely green, using sugars, using surfactants that are taken from olive oil, and they have properties that are very attractive. They can change the viscosity of the fluids on demand, essentially. Work Package 6, this is a contribution from Geomicon, a small and medium enterprise based in Germany. They developed new software to study fluid transport. Work Package 7, they manufacture new materials. We use them in this consortium to test our understanding of the fluids in confinement. But these materials can be used in a variety of applications that are outside the shale gas explorations. For example, they can be used in catalysis. We proposed to have industrial positive effects, and our consortium has been in close contact with industry, both large conglomerates, consultancy, and also small and medium enterprises. These representatives came to our presentations repeatedly, and we use that as a manifestation of the importance of the work that we have been conducting. We can ask them when they present if what we did was of any use to them. In the long term, we have coordinated our activities with other European-funded consortium. We have a representative from Frac Risk here. Other consortia that were coordinated with were SHEAR and M4 Shale Gas. And this coordination was enabled by the input of the European Commission. We proposed some possible ways in which the legalization of the activities can be improved, perhaps, and we have compared activities across the world. So this is a bit of a summary of the impact that I think we have delivered over the past 3 years. And now let me walk you a little bit through the science and the technology that we have done. So WP2 there is Work Package 2. This activity, the main focus of this work package was to provide core rock samples for the rest of the consortium to study. So this is a map of the shale formations across Europe. And on the bottom here, I listed some of the activities that we have conducted using rocks from those formations. Of importance, which will come up in a few minutes, is a comparison between the Boland Formation here in the UK and the Posidonia Formation in Germany. You will see that the rocks from those two formations are very different. From the Boland Formation, one advantage was our association with the British Geological Survey. Adrian did a lot of work to coordinate these activities in collaboration with Kevin up at the University of Manchester. And there we have been able to access rock samples from a single well at different depths. That is critical because it allows you to figure out how the rocks change in depth. And we can do detailed studies in these rocks as a function of the depth, so that we can improve the understanding that Al gave us an overview of. For comparison, we have access to samples from different places around the world, including North America, and also some commercial samples that were provided by our industrial partners. Important point here that I was about to forget is the reason it's Work Package 12 over here is that these rock samples are available in a repository for anybody who would like to conduct additional work on them. So the way to do it is to send us an email, and Adrian will be happy to coordinate sharing some of those samples with you. We have already done that with the University in Edinburgh and the Imperial College. Let's look a little bit at how these rocks look like. So this is the work from Manchester and work package 3 in details. I always like to show this figure here. I've shown it many times so far. But the point is that on the left corner over there, that is a 3 millimeter piece of rock. And the various curves that we have here are the chemical compositions of that rock. So what you see there is that even in that little 3 millimeter piece of rock, the composition changes quite significantly. That is key for shale formations. They are very heterogeneous. And here, in this table over here, now we are not looking at 3 millimeters. We are looking at a couple of kilometers depth. And what you see there is that samples taken at different depths, B1, B2, B3, and so on and so forth, they have very different compositions as well. So by getting this type of information, we can get a feeling about how the formation changes in depth. From the point of view of producing, the experts here will correct me, but one important element is this TOC, total organic content at the end. What you want to have there is something around 8%. Am I messing up? If it is too large, you can't really produce it. If it is too low, it's sort of useless to produce. So to have a feeling of whether or not your formation is in the right window is essential to be able to try to produce that formation. In Manchester, in collaboration with Diamond, they have developed techniques that are at the cutting edge. They use the synchrotron to study these rocks, and they develop new pieces of instruments that can be added to the synchrotron to look at the rocks. Here, I'm looking at one example. Lima will give us more information about this in a few minutes. But basically what is happening here is that the rock up here is exposed to a piece of metal that is pressurized in that rock. And as the pressure changes, we have the formation of a fracture into that rock. And what happens between there and here is that the pressure increases. So as the pressure increases, what you see is that fracture propagates. I learned yesterday that this rock is from the Posidonia. And what you see is that the heterogeneity of that rock is causing the fracture to go in different directions as the pressure increases. If you do the same experiment using a rock from the Boland Formation, that fracture, instead of changing direction, will go in a single direction. That suggests that perhaps it's easier to fracture the Boland Formation compared to the Posidonia Formation. Here, I'm showing you the outcome of another experiment. This is another fractured rock. And using the synchrotron, they have been able to see how the fracture propagates from a central increase in pressure. So this will be similar to what happens when you increase the fluid pressure to fracture a formation. Again, first time that people are able to do this experiment in a synchrotron and be able to monitor how those fractures propagate. More characterization of the rocks. This is a collaboration. This is work done at Potsdam, and Johannes, I think, there he is. Johannes is the expert for these activities. Johannes will finish his PhD very soon, and I'm sure he will have plenty of job opportunities lining up. He has done a significant amount of work over the past years. All right, let me go back to the screen over here. What we have here are mechanical testing of rocks, but the main point is that we are differentiating the properties of the Posidonia rocks compared to the Boland rocks. BOS here, it's Boland, and what you see there is that when you're trying to fracture that rock, it doesn't fail. It has a very different behavior compared to the Posidonia rock that is the one in green. The one in green, when you try to break it, it breaks and it fractures relatively easy because it has a large amount of clay into it. And this graph over here, this one is a summary of the mechanical properties of the rock as a function of the chemical composition. And what our colleagues in Posidonia found was that the amount of clay or weak compound that is present in the rock is a discriminant between the hard rocks and the relatively weak rocks. So now it's possible to quantify the properties of a rock formation by doing these experiments only once rather than trying to fracture that rock. So it could lead to significant savings should we decide to proceed with the fracturing of a given formation. A little more of work package 3. One property that is significantly important from the point of view of industrial production is the permeability. So what we try to do here is to correlate the permeability to the presence of pores and the pore network connectivity inside of a rock. So these are measurements of the permeability. We measure permeability at UCL, but also in Potsdam and in Manchester, and we try to coordinate the measurements so that we have a similar understanding. And what is typically found in shale formations is that the permeability in one direction can be 2 orders of magnitude larger compared to the permeability on the other direction. That has been found by many measurements across the world. What is a little bit unique is that we are trying to correlate that permeability with a pore network. So the permeability is larger in one direction because the pores are connected in that direction. So that helps us understand where we should put the fractures to try to maximize the production and understand where the fluid might go when we try to stimulate the formation. Fluids. How do they behave inside of a rock? And perfect timing. Andrei just walked into the room. This is work that he led within Work Package 4. This is just a long list of things that we have been able to do using predominantly molecular simulations. Andrei did not start his career doing this, but at some point you were at Sandia, if I remember correctly. And when you were at Sandia, you developed the force field clay, FF. That force field has been parameterized to reproduce a significant large amount of experimental data and is now used throughout the world to conduct simulations like this. Now, Andrea, using this force field, he has improved the force field during the SXT. He's now able to study the defects inside of the clays. And using this force field as being able, for example, to predict what is the fate of the naturally occurring radioactive materials inside of the formation. That is critical if we want to try to minimize the production of those norms. Other things that we have done are listed over here. Two things that are not listed. We developed models for the kerogen, which is the part of the rock that contains the hydrocarbons, and we developed models for the clays, which tend to be the matrix that keep the hydrocarbon in places. And we heard earlier the importance of the clays. It's a computer work, the one that I just described, and many of you are going to be skeptical. How can we believe whatever comes out of the computer? I was skeptical and I still am, even though that is my line of research. So what you need to do from time to time is to validate those predictions. And what we did in the SXT was to have a specific work package. We called it work package 7 because 7 is a very nice number. And Maria is the expert over here, and she has a poster on the back, and she can give you all the details. She's able to synthesize materials, the zeolites, that have pores that are very small, similar to those that are found in the shale formations, and rather larger, so that we can study the effect of these different pores in the transport of the fluids. Okay? These zeolites are used predominantly in catalysis, so there is a lot of implications for many different applications that come out of this work. But for us, it was important to use these materials to figure out if our understanding of the fluid is reasonable. And on the bottom here, I show you two adsorption isotherms. Essentially, that is a measurement of how much fluid can be absorbed into these materials as a function of the pressure. Two different gases were used. And what we did here was to compare the experiments versus the simulations that were conducted. In one of the two graphs, there is no difference between the simulations and the experiments. In the other one over here, there is a minimal difference between the two. That suggests that at least we are on the right track. So we can begin to believe those results that come out of the computers. Or so we hope. Now, if we do believe those results, can we extend them? And this is where Maria has done a significant amount of work. I did not see Maria today. She was sick yesterday, that's perhaps the reason. She's a PhD student that she's finishing up, and I think she will have many, many opportunities for her follow-up. The idea here was to use a stochastic approach. In the subsurface, the rocks are very diverse. They change within 3 millimeters. How can we predict the behavior of fluids in larger distances? And what she did was to implement an approach that they use in the catalysis community. It's called Kinetic Monte Carlo. I put that movie up because it has a lot of colors, so it keeps you entertained a little bit. But you also have the feeling of those things changing over time. And there is a stochastic process over there that is used for that. So what she's able to do is to describe the probabilities of the gases, of the fluids, to move from one part of the rock to the next. She assigns probabilities to those chances of changes, and she gives those probabilities depending on the properties of the rock. And there, the blue and red figures, those represent models in which she put blue lines that are low permeability regions immersed into red lines that are high permeability regions. And now she can use her kinetic Monte Carlo model to figure out how easy it is for the fluids to move across those regions, which in terms of industrial interest is called permeability. And she can compare her approach versus the typical approaches that are used in the industry, the analytical ones, for example, the effective medium theory. The effective medium theory will give you exactly the same permeability in each of those four realizations. She shows that permeability is instead very different. And that is key, because we saw earlier that the permeability in the shale formations is very anisotropic. If we use a software that is giving us isotropic permeability, same permeability in all directions, we will never be able to capture the properties of the shale formations. And now she's moving forward, and the idea is now, okay, I take a look at one of these shale formations. That is an image from the literature of a shale formation in the south of the US. And she's assigning properties. Okay, the dark areas over there, they are the clays, for example. The whiter areas, they are different materials. She's assigning different properties to the various materials, and she uses her stochastic approach to come up with this permeability measurement. And what she comes up with is comparable with experiments. So we're not confident to say, okay, this is a new software yet, but I think that she has the potential to develop this into perhaps a significant contribution for the community. Geomicon has taken these materials a little further, and they were part of the consortium because of their software Roxol, and during the project, during the length of this consortium these past 3 years, they have been able to improve the Roxol. They are now able to look at a formation with the presence of original fractures in there. They use as input the permeability that Maria predicts, for example, or the permeability that Johannes measures in his measurements. And they use that to describe the properties of those rocks. And they're able to see how those fractures propagate as a function of time, and also connected with how the fluid propagates inside of those formations. These are some representative results that I'm sure Tobias can tell you everything about. But essentially, they show you how the pressure in the subsurface changes when you are pushing the fluids around, either producing them or stimulating the fractures, which is critical to get an understanding of how much fluid you can produce, but also what is the likelihood of inducing seismicity in the subsurface. Florence has looked at the hydraulic fracturing fluids. They started from the commercial ones, and they said, okay, let's make them green. So they started with Guargam. That was the first hydraulic fracturing fluid that was used. And the reason I always like to show that image over there is that the viscosity on the y-axis is in logarithmic form. And what you see there is that it changes by more than 1 order of magnitude. Those are solutions of water and guar-gum at the same amount. What changes is the type of salt that you have in there. So simply by changing the type of salt, which most of the times there's nothing you can do about, it's just present in the formation, the viscosity of those solutions changes. So what it means is that some fluids will be able to carry your propants, some fluids will not be able to carry the propants, simply because the formation is different. They are able to quantify these measurements, and they are able to use now sugars that are less responsive to those changes in salt content. One issue that the industry told us was important was the formation of scales in the formations. Okay? Industry uses a number of chemicals to prevent those scale formations. Those chemicals are not green. what our colleagues in Florence decided to do was to say, okay, let's make something that is as good as the industrial components, but that you can drink or that you can put in your skin, as we learned yesterday. And Duccio, who's sitting there and who's also graduating, and I'm sure he's looking for a job that is going to stimulate his activities for the future, has been able to do that. All right? The sugars that he used, you can drink them, and actually most of the times you use them in lotions for your skin and soaps. So talk to Duccio to figure out what are the secrets in these formations, in these formulations, but it is possible to make these things. Now, to be able to make an impact in the industry, we will need to talk more to the Baker Hughes, to the Halliburtons, to the Schlumbergers, and the similar companies, and to convince them that it's worth to give these compounds a try. Let's see where we go with that. Now, let's try to minimize the impact. So this work from Alicante, I don't see Jose. But, all right.
No, he had to leave yesterday.
All right, he left, sorry. Jose and this group over there, they did a lot of optimization work. This is, to some extent, it's traditional chemical engineering work. We have the composition of the production water. Can we find a way to reduce the cost of treating that water? And the answer is yes. But the key here is to take into consideration also social aspects and environmental aspects. So I like this figure over here because in those three circles, they're looking at optimizing the cost of the operation, the environmental emissions, and also the social acceptability of the operation. And what you see there is that there is an intersect. It is possible to conduct these operations so that everybody is relatively happy. That is the key. And what was critical to observe that happy region was that the need of reducing the use of fresh water. And in these two charts over here, what they did was to analyze what are the various elements of the water treatment that affect the cost and that affect the environmental consequences. And what you see is that the major compound of each one of those aspects is the transportation of the fresh water. Okay? So these are analyses that can allow us to reduce the environmental impact of the various technologies. The other risk that often comes to mind is that of induced seismicity. This is work that Richard did, building up of work that was done in the SHEAR consortium. And this is essentially an overview of seismic events that happened across the world in the recent past, and as a consequence of a number of human activities. The human activities are listed over here. There is mining there is geothermal energy, there is water impoundment, there are dams, there is also shale gas formations. The events that are related to shale gas activities are in China, in this country a few years ago, and in Canada. And in the paper that Richard recently published, he analyzed what happened in the various situations, what was the cause of those events, and what was the possible cause of those events, and what were the implementations from legal aspects that were done in the various situations. For example, in the UK, those events led to a stop of the activities for a few years until the community better understood what was going on, and now we'll see what will happen in the next few weeks. I also like this slide because down here there is a summary of the traffic light system that is implemented in the various countries. And this, on the left over there is the current traffic light system in the UK. And we compare that to traffic light systems in different regions. So when the red light shows there, essentially the recommendation is to stop the operation. And what you see is that in the UK, the operations need to stop when the induced seismicity is of magnitude 0.5. By comparison, in California, that same red light is at 2.7. So what you see is that the legal approach changes in different parts of the world for different reasons. And later on today, we will hear what the Environment Agency decided to do in this country. Induced seismicity, we did not just overview what happened across the world. We also tried to understand what were the causes, and we developed different models. So Richard's model is on the left, whereas the model developed by Geomecon is over here on the right. They're both analytical models. Richard's model has a point pressure from which the fracturing fluid propagates into the formation, and is trying to figure out how that propagation induces or could induce seismic events. Whereas the model from Geomecon is also analytical, but it starts from a description of the existing faults in the subsurface. The other risk that we considered explicitly was the possibility of a well blowout, and this is essentially a fluid dynamics model that looks at the escape of natural gas from a well. The model was applied to a case study in the north of the UK, so we took into consideration the geometry of the wells, the geology of the situations, and what could be the worst case scenario in terms of production of hydrocarbons from that well. Then for this type of studies, what you need to do is always consider the worst case scenario. So you don't consider any one of the safety devices to actually be working. And what happens was that we estimated the explosion of that well with the fire starting. And what they did was to look at how the radiation propagates from that well. And the results from this analysis was that the existing recommendations for hydrocarbon production, they seem to be best practice recommendations. So by sticking to those best practice recommendations, we should be able to limit the worst consequences from these events that are not very frequent, but they can happen. I also mentioned the possibility of comparing technologies, for example, natural gas compared to coal and so on and so forth. Here, we use the life cycle assessment to do that, following recommendations from the European Commission. And what the point that I'm trying to make here is that graph over there with the blue charts. It's estimating what is the fresh water that is being used to produce a given amount of natural gas delivered to the user. And you see that those bars change depending on what is on the x-axis. Well, what is on the x-axis is essentially how much gas you can actually produce from a given well. So in summary, if you produce significant amount of gas from a well, you actually reduce the environmental impact of that specific production. So what I learned from that's my individual interpretation, is that if we learn how to produce more of the gas that is in place using environmentally friendly approaches, we might actually be able to reduce the environmental impact of natural gas compared to that of other technologies. We also provide some recommendations, and essentially we need to figure out what is the best way to bring about this environmentally conscious production of shale gas. We will learn what the UK has implemented in the afternoon. Gary, thank you for giving that presentation. From the European point of view, what we learn is that it is not possible to force the member states to adopt any sort of approach, but the European Commission can emanate the directives that can lead to the various member states to implement the various approaches. And what we recommend is to take into consideration the need of the public and what is the response of the stakeholders that are in the vicinity of the various operations. During the 3 years, we have done a number of synergisms and outreach events. Shaleology is one of them, one of the most successful. I learned today that more than 80 people registered for this specific event. Thanks all of you for being here. Many other events are listed there. One of them is the master's program, Global Management of Natural Resources. We have the students of the new year of the Global Management of Natural Resources in the attendance. I will kindly ask all of you to stand for a minute, the students. please. Excellent. This is for us to see who you are. We know that in about a year time, you will be looking for jobs or further studies opportunities and so on and so forth. The scope of this meeting today is for you to ask as many questions as possible and to make connections with people across the room that are from industry, academia, across the world, and so on and so forth. So please don't be shy, ask as many questions as possible. Thanks. You can sit now. With this, I shut up. I think leading this consortium has been an honor. We have done a lot of good work, I think, and I think I hope I convinced you that of the quality of the work that has been conducted. What you see that today we have invited people from many other consortia, and the reason for that is that we want to compare and contrast and learn from activities that have been conducted across the world. With this, I shut up, and I wish you an enjoyment for the rest of the day. I can. I'll be happy to take some questions.
Good. If anybody has questions for Alberto, perhaps related to the course that he's going to be teaching to you.
Yep. Wait for a microphone, please. Everything is being recorded, so that's the reason we are using the microphones.
Hi, my name is Umair Tariq. I'm from Kappa Engineering. I have two questions. One, you mentioned about the improvement or the suggestions for different frac fluids where the viscosity is not, has a different relationship with pressure and the amount of reactiveness it has with the formation salts. Is that still experimental, or have you actually implemented it in a commercial, in a real well too? What has the response been from companies like Baker Hughes and Halliburton in terms of cost and the willingness of users to bear that cost, or the willingness of operating companies to bear that cost? And what is the level of cooperation between your consortium and operators and research institutions in the US who probably have a lot more experience with operating shale assets?
Great question, and hopefully you will help me answering some of that. Unfortunately, the people from Florence just left. The poster is there. So the work is experimental. What they've done is developing these formulations in their labs in Florence. The work gum, of course, is not going to be used because that was the first generation of fracturing fluids. But the new ones are much more attractive. They use the surfactants and the other sugars. Interacting with our advisory board, where a good number of companies are represented, what we learned was to tune the concentration of the various chemicals in a way that the cost could be reasonable compared to existing fracturing fluids. So what they did was to change the concentration from the original forms to the new ones. And what they use now are, at least the concentrations are consistent with the industrially used compounds. The cost, hard to tell, because, of course, we are using pure compounds for the experiments, whereas the cost will be much cheaper for compounds that can be used industrially. It needs to be tested whether the industrial compounds will still have the same properties, but most likely the answer is yes. Building also from suggestions from the advisory board, in the midterm review, what we also did was to collaborate with people at the University of Huelva to conduct experiments at high temperature and high pressure to test whether the properties of these fluids were affected. And the results were that actually not so much. So in principle, the properties of the fluids are going to be okay when they are going to be used in the subsurface. And I trust in the poster that is still here, I have those data to show you if you are interested. Discussions with industry, that's where we have had many discussions. So we discussed with all those that you mentioned, except Schlumberger, because we never had a chance to. But since you're here, we can initiate that discussion. There is interest. Other industries that you did not list have showed interest. We had conversations with them. The testing in real scenarios is a little difficult because, for example, the operators are usually hiring contractors for these activities, and my feeling is that they stay a little bit away from the chemicals that are being used, and it looks to me like what works is used many times, and it is a little bit difficult to try to implement new activities. So I think that is exactly where we are at the moment. We need to make that connection to test and to show whether these compounds can actually work in real settings. Should that be the case, there is potential for patenting these compounds. But we can talk more offline if you are interested in doing that.
Thank you. We should move on. At this stage, John, welcome. John Shaw from Alberta, Canada, is going to lead the discussion in and around the next few talks from now for the next hour. And we have a long session this morning, we know, but there's some very delicious food waiting for you at the end of the journey. So John, would you like to take over at this point?
I'll launch the next session.
Thank you.
So good morning, everybody. My name is John Shaw. As Adrian said, I'm from the University of Alberta. My role today is to keep our session on time and to moderate the discussion if there's any need to moderate. So we've had Alex's really enthusiastic and excellent overview of the Weald Formation, an area where I had a chance to go hiking, rambling, I guess, or walking this summer. And it's a beautiful area. I was wondering how it was formed. I now know. And we're now going to turn our attention to the Boland Shale play. I would like to ask, I guess we've got Kevin should be here. Why am I not seeing Kevin? Kevin? Pardon? Where's Kevin? Oh, I see. Okay, so you're Kevin. Okay. So Kevin's bio is on the list. Welcome. So have a seat. And I'll get to you in a second. We also have Thomas and Ross who are here, and they have bios as well. You don't look anything like your picture, but that's okay. I'll have to get you to introduce yourself briefly, and then Adrian, I saw you over here in the corner. You can join us at the podium as well, and so. What I'd like to do as well is to ask all of you to hold your questions for the discussion period at the end. Yes, so we've got all our bios now except yours, so I need you to introduce yourself clearly and just say a little bit about yourself, and then we'll begin the process. So please just introduce yourself.
Thank you. So my name is Lima from University of Manchester. So I was involved in this ShaleX project as a postdoc. And from last year, I moved to a NERC fellowship in University of Manchester. So Kevin Taylor cannot make it today, but I will give this presentation of this. Shall I start already?
Not yet. No. So I just wanted to make sure that we had at least a brief bio. So that's perfect. And so what I'd like to do is everyone will have 20 minutes at I'll give you a 5-minute warning. If anybody hears my antique car horn, we know we've gone over. I'm not going to be slavish about timing because I think we'll have plenty of time for questions and discussion. But if you hear that, then that's a problem. So let's begin with you. And so I'll record the times. I have to go get my my pen, but please begin. Thanks. I can see my pen.
Okay. Today I'm going to present our work involved in ShaleX project, which names from multi-scale characterization to prospective assessment. So here is a group of people we did in this work. So majority of this work done by University of Manchester. So we all know shale is very heterogeneous and porous. So we want to use multi-scale characterization to look at the different fractures at different scale. For example, if we go to field, we can see some beddings and microfaces. And when we zoom in to look at some sections, we can see some fractures. And zoom in again, we can see some minerals and matrix. And zoom in the matrix, we can see some organic matter and some clay minerals. And all of them at very high resolution at nanoscale, we can start to see pores. So that's why we want to look at using multi-scale characterization to look at the samples. And traditionally, we use 2D images like optical microscope, SEM or something to look at the rock samples. But when we want to look at some spatial distribution, connectivity, or some topography features, 2D image is not enough. So we move to 3D to add another dimensions to look at some connectivities. And based on the 3D image, if we want to look at some physical deformation, chemical reactions, or some fluid features, we want to look at 3D. So in this work, we use multi-scale and multi-dimensional images to calculate the rocks. So we define 5 scales in our images. The largest one, we use X-ray tomography, and we call it macro scale. So the sample size we're using is like 60 centimeter, which is a core sample. So we can look at some fractures inside of this. And then the next scale is mesoscale. We use micro CT and use samples of 1 or 2 millimeters. We can look at some big pieces of mineral grains or some very big organic matter. And next scale, we call it micro scale. We use nano CT, which uses samples is 65 microns and have resolution of 100 nanometer. And next scale is called FIB. We use FIB, which is a 3D SEM technique. We can use samples of few microns and with 10 nanometer resolution. And the highest resolution we can get, we use TM tomography. It can get some nanometer scale. So the highest resolution we present here is about 0.6 nanometer. So through these 5 scale, we can understand the shale better. So this is an example of our multi-scale characterization. So from the biggest scale, we can see some hydraulic fracturing, and then we can see some natural fractures, organic matter, granular minerals, clay, and the pores. So at all these scales. And based on 3D analysis, we can have some 3D plus time, which is 4D images. We can give different temperature to look at the rocks react with temperature. And also we can look at some fractures and the deformation, which is with some different load. And also we can look at different fluid behaviors, chemical reactions, and these kind of things. And when we use synchrone, it can get very high speed, which we can scan one sample in just a few seconds or a few minutes, and resolution can get some micron scale. So this is an example of our lab. So the X-rays go through here from synchrone, and the samples go from here, and then we'll have detector go through here. So, and this is a rig we are designing. So it can give different kind of deformations to the rock samples, and we can look at fracture propagation or deformation or something. And this is another mechanical task called double torsion. And recently, we are designing an in situ hydraulic fracturing rig. So we'll give temperature and the subsurface temperature and the pressure, and to look at how the shale, the fractures propagate during hydraulic fracturing. So in terms of assessment of the prospect, there are many parameters we can link to this. But in this talk, I select 3 areas which we think is more important. The first one is organic contents and network. It will link to gas generation. And the second one is pole system. It can link to gas storage. And the fracture propagation, which can link to the productions. So first of all, we can look at some organic matter network. So we select some samples with different TOC, high, medium, and low. So when we look at the slides, you can see the dark things is organic matter. So you can see a lot of like very big dark things, which is organic matter distribution. We can see it from high TOC sample. When we look at the medium one, it becomes less, so we can still see something here, but not as much as this one. And low, and just very small and few particles, we can see it here. And when we extract these features and look at it in 3D, and you can see the organic matter, they are like very thin long banding. It's not like massive as we imagined. So in this, we can see the big organic matter become less, but there are still some small particles around. And this one just have very few particles. So we test the TOC, different TOC samples, and we found in this kind of samples, when TOC is higher than 6%, and organic matter can form a connected network. And also we found out there are two majority of the geometries we find in these samples. So one is this red one, which is very big and but very thin. So we call it the laminar masses. And also these very small things are marked in green. So it looks like very small but spherical. So we think they are linked to different kind of organic matter types or minerals or something. So they will have different abilities to generate gas or host gas. So when we look at NCM, we can see, for example, these two kind of organic matter, they have different features. If we look at this one, you can see there are a lot of pores inside of organic matter. But in this organic matter, we can see there is nothing inside of organic matter, but we can see something around organic matter. So when we look at the whole samples, we define 4 phases which associate pores, which is porous organic matter, this one, and non-porous organic matter, this, and clear minerals, and granular minerals. So there are 4 types of pores which are associated with them. We define them as intra-organic pores, which means pores totally inside of organic matter. They are generated when the kerogen maturing. And there are some organic matter and mineral interface pores. We think this may generate because of shrink. And some pores between minerals, we call it intermineral pores, and some pores inside of minerals, we call it intramineral pores. So when we look at these 4 pores in 3D, we can get the information of this. So it looks like intra-organic pores, organic interface pores, intermineral pores, and intramineral pores. And then we can extract them into some simple models. So we can see all these red are the pores, and the other colors are the phases associated with them. So for example, these blue ones are organic matter. So you can see some pores inside of organic matter, beside organic matter, and also between clear minerals and inside from granular minerals. And this is how they look like, and in separated forms of pores. And also, we can give some simple models based on the calculation. So these 2 pores, they are more like spherical, and these pores, they are more like a curved length, and this one is more like a wedge shape. And also, we can quantify the coordination numbers. We can look at the connectivity and network of the different pores. So we find out the pores inside the organic matter, they are very big, and they have very good connectivities. The coordination number is always like 3 to 5, which is very high. So it gives a clustered shape of this connectivity. And the clear mineral pores, they are quite small, and they are quite thin, elongated. So coordination number is 2. So they are not very good connected in the vertical way, but they are very good connected in the horizontal way, which is along the banding. So coordination number is more than 2. So when we look at all these samples in a bigger volume, so we can find out these clear mineral pores, they always contribute to globally connected networks all through the samples. And these organic matter pores, they are very good connectivity locally, so just within some organic matter particles. So this pore and these pores, they contribute most in the whole network of the samples. Also, we can look at the pore size distribution. So when we look at the pore size distribution, we can find there are 3 small peaks during these samples. In this sample. So this one, we can see it's very big in numbers. So this is most of the pores below 10 nanometer, so they contribute most in the numbers. So but although they are quite large numbers of these pores, but they don't contribute a lot in the network or the storage. So if you look at this one, so from 10 nanometer to 100 nanometer, and they are contribute most in the pore network. So pores in this size, they are very good connected. And the pores above 100 nanometer, they contribute most in volume. So if we transfer these figures to volume percentage, you can see majority of the volume is contributed by this pore, by this peak. So we think these pores, they have like a majority of the storage, and this pore, they have the majority of the network, and these pores, they don't contribute a lot. And also, based on this understanding, we want to know how the fractures propagate, and can they link all these pores into a higher, better connectivity. So, first of all, we did an indentation test to look at fracture propagation. So if you have indenter here, and when the load going this way, we can see some rocks are crushed just under this indenter. And then they will have some cracks in this zone, and then they will have some deformation in this zone. So we can use this to calculate all the information we want. And this experiment was done under beam under synchrotron. So you can see this is how it looks like. So the sample is here, and the indenter is here. So this is just the cameras we are looking at this. So if you look at one of the samples which Albert have showed you before, so when we give the load, and the first cracks go through here, and then they change directions at here, and the second cracks and just directly go through here, so create another bunch. So when we look at original samples, we can find out actually this sample is very laminated. So you can see two obvious layers around here. So when we give the load, the fractures go through here, and it changes the directions at the interface of two layers. So when we have the sample with very good laminations, and these things always happen. And this is a Huntsville shale in America. And compared with a very homogeneous rock, which is Bolen shale, we did the same test, but we found out the fractures just go straight to the boundaries, and it doesn't have any change directions like this. So yeah, it proved the microstructure can control the propagations of the fractures. And also, we found out the fractures behavior is quite different when we give subsurface conditions. So if this is one experiment we designed using in situ hydraulic fracturing. So we will have temperature and pressure, which is the same as subsurface conditions. And then we give some injection of pressures which simulate the hydraulic fracturing. And we can have fractures propagation. This is what Alberto showed you just now. And this is how it looks like in the synchrotron. And this is how the room setting up of the experiment. So we can see the fractures, they goes up, goes down, and then it change directions at the interface as well. It's basically the same with what we see just now. But if we have samples with previous pre-existing fractures like this, so if we give it like room temperature and room pressure, you can see there are some cracks like this. But when we give it confining pressure, and we can see all the pre-cracks closed. And then we give the high injection fluid fracture again, and some previous cracks open again, like this, and some new cracks happened. So which is look like this. And then when we increase the confining pressure again, all these cracks close again. So this is majority of the work we have done. So we proved the multi-scale characterization is very powerful to assess a prospect of the shale reservoirs. So we give 3 examples, which is organic matter, persystem, and fracture propagation in this presentation. Also, this characterization method have potential to be extended to larger scale and more complicated conditions. So this is the group we work. Thank you very much.
Well, good morning, everybody. Thank you, John, for chairing the session, and thank you for SXT for hosting another great forum on shaleology. I'd also like to thank Alberta and Adrian, because they got me involved with SXT in July and August this year. And basically, it's been very exciting seeing what the research has been going on. And as you've heard, and yet to hear the rest of the day, shale gas needs a lot of research. And above all, some critical thinking about how we can capture the full benefits for the future generation, something I call governance, as we call it. So this image might look like a rock face, if you're to the geologists present, and we are in the Geological Society. But to engineers, this is actually a hydrocarbon petroleum factory. Through man's ingenuity, and it's been mainly manly up to date, which hopefully we can maybe change. But we've been drilling long and horizontal wells and doing quite substantial intensive fracking operations. But now commercial shale exploitation is now possible on a global scale. This once deemed impermeable rock through fracturing creates effective conduits for flow. Exploitation is all about flow or reserves. And basically reserves are basically what we expect to be produced both economically and technically. We've been so successful exploiting planet Earth's natural resources that we've created now planet oil with some 6 trillion barrels of technically recoverable reserves, a truly abundant resource. Of that, to date, we've produced around 1.4 trillion barrels and have another 1.5 trillion, which is basically proved or proven reserves, so all ready for future exploitation. Exploitation of these tiny packets of energy, however, today is not as important as stewardship of these abundant natural resources. If exploitation is about flow, stewardship is about stock or in-place resources, in other words, the pay zone. Stewardship is now the main game as we transition towards climate change abatement with the goal of having some sort of sustainable ecosystem. So basically the people, prosperity and planet. And as we've heard today, shale gas has run up against the people issue in Lancaster. And there's a lot of restrictions that they're imposing on operations that 20 years ago when I was up there doing fracks, it was a different place. Governance is also not the only player. Governance is also not the only player. There's also governess, thinking about the next generation's energy or power needs. And this is getting more and more important. Today we have real choices to be made about how sustainable our future energy sources can be. So when we're thinking about stewardship, the pay zone, and its commerciality today, there are many more issues that exist today than basically Quadrilla encountered in November 2011 when they stopped their operations because they became truly newsworthy. So to assess the pay zone, you need to understand the net attributes, the net technical attributes, and today I'm briefly going to talk about 4 of them. The evidence of the pay zone is critical because without that you can't actually make a technical discovery. You need to actually flow hydrocarbons to actually claim you've got a discovery. You need to do modelling because you need to book reserves based on economics. And you need to carry out what we've heard today, experiments in the lab. And also you need to do experimentation in the field because each shale province has different challenges and opportunities. So basically I'm going to cover these topics with some brevity, hopefully in plain English. A couple of my slides are in plain maths because I have to apologise to the geologists. I'm an engineer. I do struggle a bit with plain English. In July 1985, I actually organised the Kirby-Mispleton 1 frack, which I think is still the last successful sand frack in England. And I don't consider Presil 1 was a success in many ways in 2011. It caused lots of issues. So as Alberta showed, there's basically a lot of EU shale gas resources, as well as the UK potential. But due to societal concerns in France, Germany, and Spain, they have basically zero operations. But IEA predicted that in France has actually 5 times more shale gas resources than in the UK. So it's not really surprising that the EU is interested in funding shale gas research, because they have a lot of potential still. So SXC has also been thinking about new concepts to try and aid future policy for European shale gas potential operations. So concepts, as Alberta mentioned, about worthiness, built from sustainability assessments, and also a societal license to operate, SL20, built on openness, fairness, governance, aided by masterly audits. So maybe in the future, some of this STX embryonic thinking may actually turn up to help the new pay zones in France, Germany, and Spain, which at the moment are stuck. So hopefully maybe by applying these new thinking, we might be able to move those forward. So in September 2017, UCOG put forward these numbers, and they're quite enormous. Basically, they were saying that the UK shale gas should provide half to 1 TCF a year, and they calculated that they need approximately 400 well pads. And on each pad, there's basically 10 wells, so that's 4,000 wells to be drilled. And Ernst & Young calculated that it generates some £33 billion of investment to do those 400 pads. But what is the evidence behind this? So it's quite interesting that actually on the 5th of August this year, Cordrilla said it's not possible to estimate the amount of shale gas the UK can produce until there's been some exploration and testing. So that's quite key. So a lot of these numbers have come out without true data. And if you actually look at some of the reports, they basically say, well, we don't know that. We'll just use US analogues, which is actually quite dangerous. So the reason why you need exploration, because you've got to actually prove you've got a net rock. And the reason why you need testing is you need to find out you've got a net pay. And that's pretty critical. That's what we're going to talk about. Anyhow, there does seem a shale zone trilemma. So basically, we've got North America, which has proven commercial productivity. It also has economies of scale. So in the Permian Basin, there's some 400 drilling rigs. So they've got both. So in Shale Argentina now, actually in July, they finally all admitted that they've got commercial productivity. The trouble is they don't have economies of scale, so they've only got some 40 rigs drilling. And they actually have to import proppant sand into Argentina. So they're now finding they're coming up against infrastructure problems. And also they're now filling up all the pipelines. When Poland, as we've heard from Alberta, basically is a bit of a problem. So that had no commercial productivity. So where does the Boland Shale sit? Well, until about 2 months ago, it was stopped, basically, from the last frack. But it sits somewhere in that range of uncertainty, somewhere between Poland and Argentina, I think. So it's been great to actually have these research programs into shale, because it's actually shone some really quite insightful light. And you've obviously seen this work done at Manchester University. That's quite leading. I personally think I was up there on Monday. But anyhow, on the 24th of July, the Lower Boland's now been agreed to be fracked. And on the 19th of September, the Upper Boland. So basically, it's quite interesting now that we've now got to a stage when we can actually get back into the field, which is obviously where I prefer to sit. And obviously, the crucial thing is what are these fracks going to do on a 30-day basis? Because it's not the instantaneous rate. We want to know what's happening on the 30th day, because that actually shows you some flow, more flow from the formation rather than just a frack. So what happened with Poland? Well, according to this 2011 slide, Poland could have actually organised the World Cup because they actually had enough gas reserves as Qatar. And these are quite clearly stated down as reserves. As I said, that means they're both economic and technical. And actually, 187 TCF is some 60 years of production for the UK. So what went wrong there? So basically, that's a bit of a tragedy. I call that tragedy of an outcome. Because obviously these reserves, and I don't know why, basically these two companies were misquoted, because I can't believe they thought they were reserves. But that's what happens. So we need to have a look further at that. And so those on the MSc course, you're going to learn about natural resources, which is fantastic, but you're also going to come across the excesses of exploitation, and some of these things you're going to hopefully come across and touch on your MSc. But I'm going to talk about tragedies of outcomes. And the other thing is Professor Sachs came up with these 17 Sustainable Development Goals, but actually stewardship isn't part of those. So to me, stewardship is the journey, sustainability is the destination. So it was interesting 3 months ago on Twitter, Professor Sachs was saying that the sustainability goals weren't delivering as well as he'd thought. Anyhow, that's the academic side for MSc. Move on to the reality. So in BGS and DEC in 2013, in the blue area, the whole of the blue area, they calculated that the P50 was 1,329 for the Boland Shale. So that means you can produce up to 50%, but you could produce more than 50%, but you should produce up to 50%. But the issue is that people don't point out is that obviously within that blue area, not all of it's licensed. So about a year ago, I think it was August 2017, John Underhill pointed out that actually it might not actually be the gas originally in place, which they're calculating these numbers. The gas initially in place might be a lot less. And so there's been sort of a year of throwing hammers at each other, but the geologists are still sort of debating that. Engineers, we throw spanners, which is really why I want to talk about P-well, because I'm not too sure what John pointed out, why that's controversial at all, actually, because I think what he said was quite true. So net rock is about connected porosity, and net pay is about sufficient permeability to flow hydrocarbons. So here you can see the Boland Basin. It's actually concertinaed between the coastline and the Lancaster coalfields. So first of all, you can see that actually the Boland Basin, where Quadrilla are operating, is quite a small basin. Basically, this goes offshore. And you can see John's point that actually the upper Boland Shale actually could leak into the Sherwood Sandstone. And the same with the lower Boland Shale. So the gas numbers they've calculated might not actually be the gas initially in place when the license were awarded. But you can see that industry seems to know what they're doing because they're drilling wells where there should actually be a seal. And the other thing is that we've only got core data down to 9,000 feet. So actually the deeper stuff we haven't cored. The other thing that was in the report that doesn't mention on page 45 was actually that DEC calculated what the Boland Shale should yield, basically production. And if it's analogous, the Boland Shale, to the basically the Barnett or the Antrim Shale, it should actually deliver 4.7 TCF or 2.1 TCF. So if you actually divide the 2 to 4 TCF by 400 pads and 10 wells, you actually end up with low flow. You end up with basically 0.5 to 1.2 TCF a well. And actually, as we said with reserves, they need to be economic. So if you start discovering this stuff, then the reserves are coming down. And in fact, the recovery factor, based on the report, the DEC issued was 0.2 to 0.4. Obviously, once reserves are discovered, and you have a flow rate, actually the resource characterization and description is actually covered by standards. And COGI actually is one of the only ones that actually the SEC and PRMS doesn't, but it actually explains what an analog reservoir is, and it has to have similar reservoir properties. And as I'll show you, the Boland doesn't have similar qualities to Barnett or Antrim, which is the next bit. So the crucial thing are these things. So basically, the net rock is all the rock that's connected porosity, and obviously in a shale there's a lot of unconnected porosity. The net pay is the rock with sufficient permeability to flow. Obviously, there's a lot of rock that might have connected porosity, but basically might be very low permeability. Net reservoir is basically where the net pay is connected to the wells, the well stock. And the net landscape is obviously how much has been licensed and how much from each pad that you've got, how much you can drill. But the crucial thing is you need evidence of the pay zone before you can claim that this is actually discovered. So you need a flow rate. So this is a very good report, paper written by Clark and Turner. So Clark's at Quadrilla and Turner's at Aston University. And here you can see actually the UK Boland Shale and the samples that it had was actually about half the porosity, so around 1 to 4 rather than the US shale or the Algerian shale. But also you can see that the permeability is basically a factor of 10 difference. So we're looking at about 10 to 80 nanodarcies versus about 200 for the US, and obviously some of the US is more. But the issue is once you get down to the low permeability, obviously the porosity is low, so should you actually provide a net pay cutoff? So that's an issue. but also obviously you're starting to talk about the permeability of rock salt. So maybe you should need to provide some cut-offs. So Quadrilla have basically calculated that a 2.5 kilometre well should produce 6.5 BCF. So luckily I'm a reservoir engineer, so you can actually calculate what the daily rate is. And actually this gives that. So the Quadrilla predicts that after the frac they should get about 20 million scuffs a day, which actually declines on the 30-day to down to 15. But clearly that's pretty high considering that it's impermeable rock. But the crucial thing is when they do the frac is what happens after the 30-day. The other thing, those are technical reserves, they're not economic reserves, so you have to provide some sort of cut-off. So actually the numbers could be less. And also that within the gas gets produced, there's a tiny amount of water, that over 30 years of production you end up with water pooling and basically water blocking. Water blocking is basically the water gets squeezed into the formation when you shut the wells in. So we know that from conventional wells. So we're still on a learning curve for that. Now, those doing the MSc again, basically we've got 25 licenses from Kappa. So you can run Rubis simulation and you can do this work for yourself. The models are built. So when you're on the course to use Rubis. But basically 4% porosity for about the well lengths that they're going to frac and how they've currently drilled, you should actually produce about 1.7 to 3 BCF. And that was key because in STX for the life cycle assessments, we assumed 3 BCF was the number for the life cycle assessments. So this work, I think, supports it. Anyhow, good luck with those who want to use Rubis. And Tope's actually in the audience, so if you want to talk to him about that. So finally, let's talk about this tragedy of outcome, because we need to think about what happened in Poland. So there's 4 types of reservoir effective outcomes. There's obviously no flow, which actually is more complicated than you'd thought no flow was. There's low flow, which you could sort of indicate, as I talked before. There's obviously economic flow and commercial flow. And obviously these companies, they want to make commercial flow. So obviously you need to have quite a good reservoir. So if you're a geologist, during the exploration phase, you usually do PG, which is basically the geological risk. And this is where John Underhill got involved, because basically you'd have thought, because you're drilling a source rock, there'd be loads of gas in it, and so PG would be close to 1, but actually what John pointed out, that actually it isn't close to 1, potentially. But I want to show, I need to show some numbers, because actually I think it's more down to P well. So actually if you take out the PG and call that P well no flow, then you've got 4. So there's 4 types of thing, and obviously you need to risk those 4. So what is no flow? Well, no flow basically means sustained flow, so no flow actually means somewhere between probably 1 and 10 barrels a day. It's funny, in the North Sea when we had viscous oil fields, it was actually 100 barrels. So on the Captain field, they drilled 27 wells before they went horizontal. So there's 27 E&A wells before they actually claimed that Captain was a commercial success or technical success. So no flow isn't really no flows. It's probably about, you have to produce probably about 20,000 scuffs before you've actually got, you can claim you've got sustained flow. But it's certainly more flow than just putting a core in a bucket of water and saying we've got gas bubbles coming out. So now we can risk the numbers. So the, as I showed before, the deck numbers were 1,329, which basically is the sort of gas originally in place, and that's obviously unrisked. So you'd use a PG of around 20%, and basically a P well of about 75%. So we've got 4 types of P well. Let's just assume that the no flow is 25%. So you multiply that out, and you basically end up with 200 TCF risk skip, which is why I'm not too sure why they were so cross with John to point out that actually there was a geological risk. But if you use 30% recovery factor, that means you've got somewhere near to 60 TCF. So as we only use 3 TCF a year, that's 20 years of production. Obviously, if it's 15% recovery, you've got 10 years. But as we've seen, you've got 3 BCF a well. So say 10 wells on a pad, that's 30 BCF. 30 BCF, divide that into the 60 TCF, that's 2,000 pads you need. So you need 20,000 wells. So you need far more than 33 billion investment. You probably need the same size as BP, net market capitalization. And if you did have 40 pads, you'd be basically producing 150 BCF a pad, which certainly isn't what Quadrilla is predicting, and certainly what we didn't use in SXT. So after all that technical stuff, it's actually the net landscape. It's how many pads you can get hold of. And basically the question is, if you're going to have all these pads, you're going to have economies of scale, so you're going to need 400 drilling rigs. So let's think about the the potential outcome, and this is a probabilistic distribution. This is really what the geologists use for PG. They have to make sure that the characteristics they're using to describe the P10, P50, and P90 case actually sort of fit on this distribution. So the good thing with log normal is you only need 2 points. So if you actually use the P99.88 as the 20 scuffs, which is discovery, and you put in the P10 of 60 TCF, the P50 actually works out at 90 BCF, which is only 3 pads, or 30 wells, or maybe 10 pads with 3 wells. And that's assuming that actually you've got a nice sort of competent conventional reservoir. So what sort of happened, I think, in Poland is obviously the P-well non-flow was actually a higher chance than people realized. So I think they were focusing more on these massive numbers of resources in place rather than actually what each well could produce. And if you do then obviously the P50 is minuscule. So that's effectively what happened in Poland, I think. Anyhow, this is what we teach you at Shaleology. So 1,329 times 20%, 75%. So that gives you the 200 TCF. If you use the, it's got 2 slides, John.
Sorry, finished. I was trying to get it to stop.
It's very nice music, huh? So if you use the 2 to 4 TCF, that would equate to 1 to 2% recovery factor. So I think there's something more going on. And if you actually use a P-well of 25%, which is commercial, then you actually got 66 TCF, which is actually 3 to 7. So maybe that's why in the DEC report, Tony, I know her because we worked together on the Improved Oil Recovery Program some 40 years ago or 30 years ago, which is very good. So obviously, I think that's the sort of numbers that she was sort of implying. So the net landscape, the pads certainly that Quadrilla have, you probably could only access about 2 to 22 square miles. And so they need lots more pads. And maybe 60 BCF is a good number for 30 wells. So basically, this analysis is all based on what we saw in SXT. The issue with SXT is that obviously we haven't had the well data from the horizontal well, and obviously they haven't actually done the frac results. So it's quite nice giving this presentation, because after the frac, I've probably given just 2 slides, which was the answer. So we still don't know. And I wish Quadrilla luck, because lots of things can go right and lots of things can go wrong, but it is a truly very exciting operation to do. And you can see that the GeoIP area that DEC were using was massive, and that's why there's such small numbers. So very quickly, last one, Bowland Shale, Lancaster. Lancaster's, they wore the roses. It's a sort of noble area. For those who haven't really followed what I've said, but basically the DEC have calculated the yellow area in that flag for Lancaster, when actually you need to think about the net pay and also the natural fractures, which we haven't actually talked much about today, although we did this morning on the Witch Farm area. So the natural fractures are key, but unfortunately, when you drill the wells, the reservoir won't flow without wells and fracs, and the net reservoir is actually less than the net pay. So that's why the numbers come down. You have very, very small recovery factors if you do everything based on net rock. And of course, the crucial thing is you need the net landscape. You need to know how many pads you want. Very quickly, because I know there's going to be a slight discussion afterwards, but if you read work program 11.1, which Christine put together, is very exciting. I think it was a really good report. Basically, she talked about exploration, regulation, governance, and public assessment. And actually, there isn't a definition for stewardship legally, so it doesn't appear in formal markets, and actually governance and stewardship appears in internal markets. And it was an excellent presentation from iGas to actually tell you how they actually go ahead with stewardship. And with unconventionals, you have to do a lot more work than just conventional reservoirs, and it was really quite impressive what they're doing. And public acceptance, that is the key, because that's the people issue. So if you actually asked people in the office in this presentation here whether they think what's happening, but certainly have we had over-resource prediction? Well, massively yes. Do we have over-regulation? I'd probably say no. It would be interesting what the operators say. They might say a small yes. Same with government. But public acceptance, have we had over-public acceptance? Certainly not. But do we actually have a sustainable energy policy in this country? Well, no, but people are actually talking about stewardship. So that's happening. And the very last thing, which is a very big slide, it really is the last one, but actually DEC's numbers are down here, which is net rock. You actually have to produce commercial oil up here. The issue with the world classification is that speculative prospective and speculative resources don't exist. They actually come in from the mining. So when Tony Harvey was writing a report talking about speculative resources, And I'll leave it with you whether shale gas is actually a mining operation or a well operation. Thank you.
Thank you very much. As I said, my role is partly that of a policeman. So, but anyway, we have had 3 different perspectives on the Bolin, different length scales, different perspectives on time scales, regulations, operations, and so we have a fairly broad perspective based out of SXT and other work that's going around. So I'll invite Adrian. Really, you're still my friend. Although you did get the buzzer. I changed my mind. I decided the horn was too rude, so I thought by the seaside, having had the experience of walking in the South Downs earlier in the summer. Anyway, so we have the 3 of you. Now, Al, I don't know if you'd like to join us up here and be part of this discussion too, or do you want to just sit there or escape? It's up to you.
I don't need to escape.
I'd
rather ask some questions.
Oh, good. Okay, fine. I'm happy with that. And so the floor is open for discussion. And so I will invite people to hands up. And we have 2 microphones that will wander around. And so if anyone wants to go first, that would be great.
Yeah, well, I've certainly got.
Okay. So Al's ready to go. Perfect. Thank you.
Thanks, guys. All did an excellent job. And we did try and tell DEC that they should be risking the numbers they published, but they chose to ignore the reviewers. So it was pointed out at the time that the numbers were in the ground should be risked geologically. But there's one thing I'd like to ask all of you in terms of assessing shale plays and the sort of things you'd like to take into account when you look at them. And one thing nobody mentioned was pressure. And I'd like to get your views on whether you think overpressure is something we really should be worried about, or the absence of it.
Very good question. I like that.
Yeah, so I'll step in. Yeah. Pressure is obviously very key, and an oversight for not mentioning that. So we know that the basins have been buried deeply, and we know that they've been uplifted on a number of times. Hopefully we preserve some of the overpressure from that. So for instance, when I think about the northwest of England, we know we've got a thick shale sequence overlying our primary target. Hopefully that can act as a seal in order to keep that pressurized, the pressurized rocks below. Because as we know, reservoir energy is very key to getting those high initial production rates, and then obviously the ultimate recovery from the well. So when we're looking at drilling wells, we need to look at taking different pressure measurements as we go down and drill those wells, and so that's something that forms part of our formation evaluation program, both in the northwest and the East Midlands. So I think the data from Quadrilla suggested that they had overpressure within that area, and we know that they've had a large amount of overburden removal as well. So that hints that within these low permeability reservoirs, that high pressure interval has been maintained within those reservoir rocks. So hopefully that is the same story as what we've got going on in our basins as well.
Thank you, Tom. Any other thoughts on pressure?
Yeah, so because we did a lot of experiment work, it's not really measure the formations or something. So the pressure we're using for samples for the 3D method, we are not using any pressure. But for the 4D images, look at the fracture propagation or some permeability. So we use different pressures. We calculate it, but maybe not exactly the same as we had in the formations, but we test a few fracture range. So from like 0 pressures to very high, we test into 65 MPa or something. So we have the rock behaviors under different kind of pressures, but it may be not the same as subsurface, but we can calculate that. Yeah.
Yep. Okay.
I'd like to comment on the pressures. Basically, that was part of John Underhill's input, so I think there isn't any overpressure. So
Well, I think you'll find there is going to be overpressure.
Oh, this is why we shouldn't have.
I don't agree with John on much of what he said.
Well, This is the great news that we're starting again fracking, and it's back in the engineers' camp, and we'll find out once we do the frack. So there won't be any discussion, but if you ask my personal opinion now, and having done Kirby-Misplen, that they won't be overpressured.
Al, would you like to comment?
Yeah, I don't think, Kirby-Misplen I don't think is overpressured, having worked in that when I was at BP, but I do think we're going to find that the East Midlands, the Lancashire part piece, and the Weald will have retained their overpressure. And if you look at US shale production, most of the plays are actually overpressured. I think it's only the Haynesville that isn't, but the Bakken, the Barnett, Eagleford, these all rely on overpressure for the high flow rates.
I agree 100% with that, but we're talking about Lancaster and the Boland Basin.
I think so Francesco's work for the petroleum systems modelling showed that the Boland Shale interval within the Gainsborough Trough has generated a lot of hydrocarbons, so we have the volumes associated with that there. And we know that the majority of the hydrocarbons within that system haven't been expelled from that source rock. They actually remain in situ because of the low permeability nature of the rock. So hopefully that high generation capacity and the low permeability rock, and then the associated uplift and the shale sequences that we have above that have been able to maintain that pressure seal within that interval. And of course, when we go on to hopefully frack wells, there we should get the empirical data to tell us yes or no, is that overpressured or not. But
yeah, that's the only data it really can't tell us. We can model it as much as we like, but it's production data will tell us what the flowing pressure is.
yeah.
Okay.
Thanks, guys. Appreciate it.
Okay, thank you. So other questions or comments for the panel?
Can I ask a question?
Sure.
I want to ask Lynn a question, because you showed the Haynesville Shale. So how do those little holes in the Kerridgine look like in the Boland Shale?
So, yeah, the examples I gave is Haynesville Shale. So you can see they have a lot of pores inside of organic matter. And for Boland Shale, they have only very limited pores in this. So, and some of the organic matter pores are not connected. So it's like they only have a few ones inside of this. So compared with the Boland you mentioned, the Poland Shale, it just almost have no pores inside of this. So I think this is also one of the reasons Boland Shale may be not as good as some American shales. So yeah, this is our observation.
Okay, so we've conducted SEM analysis of some of our cores through the shales within the northwest of England and within our particular basin and the SEMs that we were looking at in that well. We saw type 2 marine kerridgine, and within those marine kerridgines, we saw organic pores within the SEM images. However, how interconnected those pores are and how much the volume is pore space throughout the whole of that source rock we're still looking into. And obviously, when we're designing our formation evaluation programs for the upcoming wells that we'd like to drill there, that's something that we're going to look into a little bit more. So,
yeah.
To
give us a sample, we'll tell you the answer.
Well, there are a number of ways we can go from this point. So one is to address the issue of sample availability for detailed scientific study on two levels. One would be samples that are kept at pressure and so on, if not at temperature, and samples literally of the rocks from the cores that are in a standard core.
Tony, you have to stay closer.
I have to stay closer to the mic. Yes, sorry. Yes, I understand. So we have a number of directions that we could go in from this point in terms of the discussion. One of them would be if we were to provide, if the universities were to provide detailed analysis along the lines that Lynn has done for the Boland, it would be wonderful to have core samples or even cores that have been kept at pressure available to researchers for detailed analysis. And I realized that in the project there were some issues around making those samples available. And this is actually an issue in terms of limiting the information that's available both to operating companies and to others. Would anyone care to comment on this? No.
I'll comment on that. So obviously when we drill wells onshore UK, the data is commercially sensitive and confidential for the initial period. After that is up, we actually have to release the data, and we've been doing that for 2 of the wells that we drilled in the northwest, and we've also done that previously for Ince Marshes as well. Those cores, much like the pre-salt one, are then taken to the BGS, where they're then able to be sampled by the scientific community after that initial confidentiality period. That data is then, when you sample those cores at the BGS, that is then available to the community as a whole to access. There's also cores as well, legacy cores from outcrop, where both operators, so we've sampled some of those cores, and I know that I've seen some of those samples actually within the Manchester presentation as well. In terms of pressurized core, it is an expensive operation for an operator to run that logging equipment to acquire pressurized core samples and then maintain those over a period of time. So that's why we run other analytical methods such as wireline core acquisition and canister desorption analysis, because that's a more cost-effective manner of getting those gap-in-place measurements, but obviously there's uncertainty around those measurements because of the lost gas. So I guess I feel that a number of wells might need to be drilled. So we've got the best practices and we've nailed down the operations. And the prices need to come down in terms of pressurized core acquisition before that's readily business practice, if you like.
Right, fair enough. No, those are all fair statements. It was just a topic that that I felt needed some airing.
John, if I can.
Go ahead. Yes.
For the records, I'm Alberto from SXT UCL here. Just to follow up, it is recognized that there is commercial importance in the information that you can get from the core samples. From the academic point of view, my presentation earlier, I showed the results from a commercial sample. In that case, for example, what we did was to study the sample and to provide information back to the organization that provided it. And we actually don't know where that sample is from. The results have been published, but we have never revealed the source of that sample. So that is one way in which we can maintain the confidentiality while at the same time pushing the research as far as it can go. We certainly appreciate the importance of those issues.
Yeah, so we've also worked alongside different institutions such as Imperial College, and also the Geological Society of Denmark and Greenland, where in those intervals we've given commercially sensitive data, which is fed into the research that they've been conducting in the different institutions, and that work has been published at EAG and AAPG conferences, and that confidentiality has been maintained. So you're absolutely right, that is one way in which we can do it, and I think that's a way in which we have been doing it over the past few years.
Because it's very important to have, let's say, new researchers, PhD students or former PhD students, and others to be working on the most relevant samples. And so this helps us prepare and train people for the next generation of staff for the industry, let's say, whether it's geology or petrogeology.
It is important to manage the process because these cores get cannibalized extremely quickly.
Sorry, hold on. Yep, sorry. Yeah, it's okay.
Yeah, it's very important to manage the process because the cores tend to, once they're released, get cannibalized very quickly, and it doesn't necessarily get the right data to the right researchers. The proposal kind of out there is that the BGS in Keyworth should manage the process. And I think I got an email from the other day with some proposals for how that might be done, so that everybody who has got a good case gets to see the right samples, and it's not on an ad hoc sort of basis.
Correct. And my impression would be that the intent is to have the best science on the highest value samples, right? And so that there is an economic benefit and a community benefit for all. And it's managing that process is the critical piece that I think perhaps needs more work, unless there is something that's really in the pipe. I think that's actually there is something in the pipe. Excellent. I think that's because it is an issue, and to have the best science, you need the best samples, and there's only so much you can do with, let's say, dead cores. Let's say. Okay. So, Adrian.
Just a comment about the length scale of observation. We're looking at a huge range of scales of observation in terms of analytical techniques and cutting-edge science that Lynn presented, for example, from nanometers up to kilometers for resources. This is a challenge for the entire industry, I think, to go from one scale to another. And one of the things that SXT has been trying to come up with some answers for is how to go across those scales. I'd be interested in your views on the panel generally, perhaps each of you, I don't know how to do this, on what you think where the focus should be in terms of effort in trying to go across these scales. Do we need more effort at the very small scale, or do we need more effort in terms of going across the mesoscale or the macro scale, if you like, the megascale, say?
Then why don't we start with you?
Okay. So most of the scales we are looking at is very small, so from nanoscale to centimeter scale. So we are trying to write a paper right now to upscale these characterizations we observed from nanoscale to centimeter scale. So this is the biggest one. The biggest range we can do for now because of the data we got. So this is across 6 scale. But I think, to be honest, in the industry or for like production perspective, maybe like meter scale or kilometer scale can be very interesting. So we are also trying to do something is linking our observations in the 3D to some log data and maybe some seismic data to use some big data or some machine learning method to extend that to that scale. But we're trying to look for more data, like logging data or seismic data. So maybe you need some of your help or something from industry to extend our observation to a bigger scale.
Just before we move to Tom, perhaps, or anybody else who wants to reply about the scale, I should have made the point that if you make these very precise studies, it often takes a year before the information comes out. And so how practical is that for industry who might want the answers on a rather shorter timescale when you have benefits of observation, but then you have to think about how rapidly it could be, or how it could be representative?
Yeah, I think that is a fair point to note. So obviously the industry hasn't moved as quickly as we'd have liked over the past couple of years, so that's enabled us to get the information in from PhDs over a period of 4 years or something like that. In terms of scale, I think, well, obviously as the industry picks up and we feel we're going to have more activity, then we're going to need a quicker turnaround of those analytical techniques in order to influence any operational decisions. So I think that is a good point. In terms of scale, obviously, you can see from my presentation where we are in the program. We've got two large areas, a large acreage portfolio, and at the minute we've been doing a regional assessment on the kilometre scale to assess where we want to site those horizontal wells, those vertical exploration wells. Once we drill those vertical exploration wells, we've got a very thick sequence to characterise, and that's over hundreds of metres of scale. After that, we then might have an individual section. So in Scafworth B2, that's 165 metres thick that we're trying to characterise. So we're doing that at the minute from wireline log data, but obviously we want to be taking core from there. Once we've done that, we want to have the landing position for the horizontal wells. Now, I know in your presentation you were talking about 10 wells per pad, but that would be at one stratigraphic interval. We have thick sequences, and the prospectivity of that might change through the sections, so there might be an argument for a stack development, if you like. But each one of those stack development, that's a specific interval in which you want to be targeting a horizontal well. So it might be a 30 to 50 metre thick interval. So again, the scale's changing there. Once we then move into where we're going to place the stages and then the frac designs of that, that's when we start moving into the metre to centimetre scale. So how do So how are we able to stimulate each of those intervals? And then once we've done that, we're now moving down to the centimetre, the millimetre, and then the micro to nanometre scale. How does the fluid react with the rocks when we're initiating that frac and after a period of time when the fluids are within the formation? But then how do the hydrocarbons flow through that media and into the wellbore? So that's the nanoscale. So at the minute where we are, I think we're on a meter scale, meter scale, I would say at the minute. As we move further down the line, we obviously need to move to the finer scales that you're looking into now, which is good that research is already being done up front. And then as operation activity increases, we'll probably need a quicker turnaround on that information as well.
So that would speak to having high-quality samples available earlier rather than later. If from the point of view, if it takes a year to get the data, then the samples need to be ahead of the need. Yeah. But I think also, yes.
Can I just make a comment?
Just something between a comment and a question. So I guess you have all the 3D seismic data and all this information. You have a structure model. Then you will have all your small-scale information from your wellbore, which I would consider really small scale. But you really have a gap between your well information, a handful of samples, and some other thinkings, the large structures. Do you foresee from your 3D seismic interpretation that you can gain some information about the other structural features in your reservoirs, like fractures, fracture frequencies, all these kinds of stuff that may make up what you stimulate and will define your targets you might want fracturing later on?
So obviously that comes down to the resolution of the seismic data, and the seismic data that we have doesn't give us the ability to map fracture networks at the moment. So what we can do is we can revert back to image log data that we're able to acquire within some of the wells that we've drilled, and then we can look at the orientations, the aperture of those fractures, and then potential fill. But then we also have to go back to the outcrop, so that was why it's really important for us to go and analyse that. And I know Al showed some of the work on Kimmeridge Bay, that wave platform, and it had some of the fracture orientations there. And I think that's a similar workflow that we are looking at doing in the northwest of England, and then also in the East Midlands, where the shales outcrop in that area. But our seismic data doesn't give us the resolution enabled to do that, no.
If I may add, have you tried looking into the seismic attributes you might derive from your seismic data, or is it so poor for whatever reason that you can't do it? Because if you say you can do mapping along your well, you can do outcrop mapping, both is perfect, and then use a seismic attribute, pinpoint it along your well and spread it out to populate your reservoir model, that might be a way to do this upscaling stuff.
Yeah, I think that's a very good point. So obviously, within our 3D seismic data sets, the current wells that we have in there are legacy conventional wells that have been drilled. So they might not have a full suite of logs. So for instance, the image log data and things like that. So when we look at drilling our exploration wells, we would then go back to look to collate all of that fracture information data, and then we would go and look at reprocessing that seismic data to see if we can pull out any of those sorts of information from the attribute analysis. So that's something that we see we would have to do down the line once we've collected more data to inform the reprocessing.
But sorry, just Adrian, directly to this point, and then it's your turn, really. But that's where I think models can play a big role. We see in the research that there's a scale dependence to the properties, the average properties that come out of the various levels of analysis. And so if the centimeter or down to nanometer scale, plus some hypotheses about the way fractures propagate or are present, that can then be scaled up toward larger scale effects that will then arise during drilling or production and so on. And so I think there's a place for ground-up modeling and then the upscaled to connect with that very fine scale, and managing that bridge is, I think, a very productive area for collaborative research between industry and academics, because that's where there's a lot of uncertainty. And I think some of the work that was done in SXT actually helps span that gap. Anyway, sorry, Adrian, it's your turn.
Thanks, John, but you just mentioned what I was going to mention. So I think modelling is key because we have a very good data set now. But I think what SXT has shown is that there is a niche for universities to have a role here. And I think if it takes 6 months or 9 months or even 3 years, then there's a benefit. And I think SXT has showed that benefit. So I hope that industry out there and other places are going to use Manchester's new kit and UCL's new kit because it's quite impressive. So obviously I've had 35 years using commercial kit, going to contractors and providing it, but it's not the same level of sort of objectives. There's more aims that they've done through the research, and actually they've come up with some quite new stuff, and particularly at Manchester going down to 1 nanometer or whatever it is to measure the pores is quite incredible. So the very fact you can do this now. So obviously I think the big role for universities is for when you go into new areas. So say France, Germany, Spain, which might be something like 30 years away from commercial shale gas production. But they need to get on and do the exploration now, because otherwise you can't end up with an argument for the societal license to operate unless you've got some data. But obviously once there is this data like that now for the Boland Shale, it's time to do, as John says, do more basically modelling. So I hope industry do realise that there is a benefit from these longer-term programs, and actually this new kit can be used to maybe provide more commercial services.
Other comments, questions, new topic could be introduced? How are we doing for time? My phone's over there and I don't want to go get it.
Bang on if you stop there.
That's really easy. Thank you, everybody. So to thank our speakers again. And our lead questioner, of course. All right.
Okay, thank you very much, John, for chairing that section, and also for the contributors from really interesting information and talks. Very good talks, thank you. I'd now like to introduce Joanna Forwalker, who's going to chair the next part of the session, also from UCL. And I should take this opportunity to thank the Deep Carbon Observatory for funding this event. The Deep Carbon Observatory is a community of approximately 1,000 scientists globally who are looking at the total carbon budget for the Earth in all its forms, both organic and inorganic. It involves industry, academics, and every avenue you can imagine, with no area of science excluded from this discovery journey. And you might hear a lot more about the Deep Carbon Observatory next year, because 2019 is the Geological Society's year of carbon. Okay, so with that, I feel I've done justice to our sponsor. Thank you. Joanna.
Hello, so I'm Joanna Forwalker. Thank you, Adrian. I was a project partner on the SXT project, particularly looking at the environmental impacts and risks focusing on the induced seismicity. So my role was really to assist Richard Porter in his modelling, and Alberto showed a bit of his work earlier. He's actually just had that published in the last couple of weeks in Wiley Interdisciplinary Reviews, so it's a great piece of work. And I must just say a personal thank you to Richard. I was on leave for 6 months in the middle, and Richard therefore took on even more work than he originally had, so thank you very much for continuing that and doing a really fantastic job. But as Alberto said, today we want to hear from people outside of the project. That includes my next 3 speakers, and it also includes all of you. I hope to hear from as many of you as possible in the discussion so that we really get your views across. So the speakers I'm delighted to introduce will be Alberto Guardini from the Politecnico di Milano. Apologies if I get any pronunciations wrong. And he'll be talking about risk assessment using a statistical approach. We'll hear from Michael Wilkins from Ohio State University on methane-producing microbial communities found in shale whales, implications for environmental and industrial risks, and then from Mike Dinkel from Anadarko on water infrastructure and produced water treatment. So 3 great talks, I'm sure, and then an exciting discussion afterwards. So I'll invite you each to talk. As in the previous session, we'll hear the talks, the 3 talks, and then have a discussion at the end. So please do write down your questions so you don't forget them as we're going along. I'll give you a 3-minute warning just by putting up my hand so you know how to carry on. So thank you very much, and hope you enjoy all the presentations. Just a reminder, please do use the microphones as it's being recorded. So I know if you have a dying question, please do still wait for the microphones and introduce your name and affiliation. Thank you.
Thank you very much for the nice introduction, and thanks for the nice invitation to expose some of our work in this forum. So let me start. So I'm Alberto Guadagnini from the Politecnico di Milano, and I would like to start by, let me say, sharing the blame about this presentation with most of the people who contributed in the past few years to all this body of work. So I started my subsurface flow dynamics and transport group something like 25 years ago, right after my PhD, and now actually the group is quite dense with people. We are 4, let me say 3 full professors and associate professors, and then a variety of PhDs and postdocs in the group. And some of them you're seeing here in this picture who contributed to the work that I'm doing, to the work that I'm presenting today. The key idea actually when we started all this work years back was to focus on competitive use of groundwater resources. And we all know, and I'm not spending too many words about what it means, competitive use of groundwater resources, especially in modern society, and that we are facing unconventional challenges which are associated with processes of varying complexities which can be found in the subsurface. Processes which are not so localized. They take place in diverse parts of the domain, across diverse spatial and temporal scales which are involved in the system. And we have properties of the system, whatever a property of the system means, and I will try to address this point during the presentation. And functions of a compositional multi-phase system. So, like we pointed out earlier, we should need for a multi-scale and multi-physics approach and series of concepts. So we should somehow be able to translate into some sort of concepts, mathematical models, and then operational tools. How can we model such a system in an adequate way? I'm not sure I know. That's why I chose a probabilistic approach. Okay. So, probabilistic approaches. The key point is to assess and to work on some effects of some operations or anthropogenically induced stresses on the subsurface on some target variables. Target environmental performance metrics can be, for example, threshold concentrations, overpressures, and some other variables of concern. We deal with complex systems, sparse data, which are spread across a variety of scales. So what do we do to come up with risk assessment, quantification of risk assessment in probabilistic terms? Well, we do like everybody does in the engineering and physics context. We simplify things. So we compartmentalize and destructure a complex problem into a set of hopefully more manageable problems, and then we try to join them by more or less simple or complex probabilistic rules. I will not go into many details of these, and the examples that I will show you are going to be kept simple on purpose, just to illustrate the general idea. Most of this work has actually been performed within the context of a shale gas related project which was funded approximately at the same time as SXT. The name of the acronym was FRAC RISK, and we actually ended our activity 1 month ago, 3 months ago. So we decomposed the subsurface actually into a set of small-scale problems, which we defined as source, pathways, for example, for contaminant migration. I use the word contaminant loosely to define any chemical species we can migrate in the subsurface. It might or might not be hazardous. That's a different point. And then the target, where by target or receptor I mean aquifers of a certain extent. So we compartmentalize and we destructure our problem into a set of small-scale, more or less manageable problems. Each one of these is associated with a conceptual and a mathematical model and is relying on data to condition the conceptual and mathematical model. For each one of these, we are going to have, unfortunately, uncertain concepts, uncertain models, and uncertain model parameters. So we come up with uncertain inputs, we come up with uncertain outputs, and I will quantify the uncertainty in the input and outputs in terms of probability density functions. So my target is I start from some probability density functions and a variety of possible models. I come up with output probability density functions, and I propagate along the way up to the target aquifer. That's the key idea. So in essence, just as a schematic of the work, we start from from studying what happens in the source. So for example, where we focus, for example, on the flux of fracking fluid, for example, fluid and the overpressure and the overburden. Then the system in the shale formation is associated with some uncertain parameters and modeling concepts. We come up with probability density function of the output here, which constitute then the input in a more or less complex way to the overburden, so flow and transport processes in the overburden. Unfortunately, parameters in the overburden are shared with parameters in the shale formation, so we have to deal with joint probability density functions of these shared parameters, and come up with probability density functions of quantities of interest in the superficial aquifer. The workflow is more or less something like this, and for the moment I'm skipping the meaning of PCE here in the figure, and I will come back to this in a bit. So I will focus on two aspects of this workflow. One, the modeling aspect, which means, in my view, at least in this presentation, the way our concept of the functioning of the system, which is based on observation at diverse scales, is rendered through a mathematical model. I will not touch the problem or the issue of model uncertainty, so I will assume in this presentation that I'm dealing with just one mathematical model, which is my reality. It means associated with more or less 100% probability of being the correct model. If I have more than one mathematical model, then we can deal with that in a Bayesian context, and I will be more than happy to discuss about that during the discussion phase. For the sake of explanation, I will focus with one model. It can be more or less simple or more or less complex. Then the key idea is to analyze the effect of the uncertainty of the parameters of that model. How many parameters do I have? Well, it depends on the model. How uncertain are these parameters? It depends on my knowledge at some scale of interest or at different scales in the system. Basic approach is to analyze the parameter space, to identify parameters which are, let me say, relevant or influential to the outcome of a model, without for the moment quantifying what I mean by parameters which are influential or not, and then come up with an output. You typically do it actually with the probability distribution of the output. You typically do it by Monte Carlo sampling. That's as easy as that. There are several flavors of Monte Carlo sampling. Unfortunately, it might involve huge computational times. That's why, as a strategy, we developed the use of surrogate or meta models or reduced complexity models. You can use any model reduction technique that you wish. In our case, we focused on polynomial chaos expansion, on a polynomial chaos expansion-based approach. Just to give you an idea of the type of output, or what I mean in this case, I'm depicting here just a very simple example where we studied geochemical compaction of a basin in the presence of precipitation dissolution. In this case, it was due to smectite light transformation, for example. So here, don't worry about the symbols. I'm not going to explain the symbols. The point was that we had a model with some parameters. And along the vertical, I have quantified in colors the importance of that parameter. So for example, this parameter here was important in this region. It was not important in this part here. What do I mean by important? Well, in this example, we use the classical matrix of importance, which is related to the Sobol indices. It means a parameter, according to that concept, a parameter is important to the output of a model when it is influential to the variance associated with a given quantity. So uncertainty, in this context, is associated completely with the variance of the system. We come up with distributions, in this case, of it was porosity in the system, probability distribution of porosity, and quantification of importance of parameters. For example, this parameter was important to the variance or controlling the variance of the porosity at this depth in a significant way. It was not important at this location. We can discuss whether or not variance is a good proxy for uncertainty. That's a different story. I will come back to that in 3 minutes. In terms of results, then, you can use and build a surrogate model with several techniques. We use, like I said, generalized polynomial chaos expansion approach. We came up with our surrogate model. We could run it more or less easily in a Monte Carlo context and come up with vertical distributions of overpressures. So at a given depth, you have a probability distribution of a probability density function of overpressure, and you can come up, as an example, with the way probability distribution of overpressure tends to deform with depth and come up with thresholds and probabilities associated with thresholds. In all this workflow, well, you have to take care about probability distribution of parameters, of your input parameters. As you know, there are several simplified models to take into account that. Gaussian, log normal, whatever model. The point is that either Gaussian or log normal actually do not work. And because statistics of parameters or natural properties actually tend to vary with scale. So they are associated with PDF, with probability distributions, which vary and transition according to scale separation and actually the scale at which measurements are taken. Therefore, what we did was we just published it and come up with a statistical model for scaling. Not much. We were talking about during the previous presentation about scaling up or scaling down properties. Since we are dealing with statistics, our idea is to scale up or to scale down the whole probability distribution of your variable of interest. So you have probability distributions at some scale, and you want probability distributions of the same quantities at the different scales, and we developed a way of doing that. And believe it or not, we were able to test it successfully along different scales. So field, transit scale. This is just a block. This is the size of 30 by 30 centimeters. These are micrometer resolutions of X-ray images of rocks, sandstones, and carbonate systems. Poor scale velocity distributions in 1 and 2 phases. And we saw that the model actually holds up pretty fairly across this range of scales. So technically, we are able to up and down scale statistics of quantities of interest. So like I said, in order to come up with a definition of risk, once you have a model or with a quantification of probability, what you should do is to diagnose your model, to come up with relative importance of parameters associated with a given model. If you have multiple models, you can repeat the same procedure for multiple models, or you can assess the variability, the importance of the parameters across models. One way to quantify uncertainty is through Sobol indices, which are associated with the standard ANOVA decomposition of the system, and tell you how the variance of a response of a model is influenced by knowledge of a parameter, knowledge of a given parameter of a model. Now the question is the variance always a good proxy for uncertainty? And of course, it is not, okay? And what we faced, what we have been working on during the last few years, was to come up with metrics defining the way the entire PDF change if I know an input of a model at a given scale of interest. So we reviewed variance-based and distribution-based uncertain sensitivity approaches, and we came up with methods, with a methodology to come up with a methodology to quantify the way knowledge of parameters of a given model tend to influence, well, not the entire PDF, because we could not, so we tried to be as humble as possible, and we focus on the first 4 moments of the PDF. Mean and variance, everybody knows the meaning. Skewness and kurtosis are related to the shape of the PDF and to the weight of the tails, which is important in risk assessment because it is associated with very low or very high probabilities in this case. We defined indices which provide us the expected variations of these first 4 moments of a probability distributions. And on the basis of the joint analysis of these first 4 moments, we were able to come up with classification of ranking of importance or degree of influence of parameters, model parameters, to the probability distributions of an output of interest. Just to give you an idea, so we applied it in several contexts, this kind of methodology. We applied it, for example, well, the first thing you do is you apply it against an analytical solution. We chose the Ishigami test function, first of all, because it has a really cool name. Second of all, well, it is. Second of all, because it is used in math it is a standard test for all uncertainty quantification techniques. So we did it. Then we applied also in the field for critical pumping rate in coastal aquifers, solid transport in laboratory experiments, reactive and non-reactive solid transport, well, within the context of our frac risk project, and believe it or not, to come up with gravimetric variations during pumping tests in unconfined aquifer systems. This part here is actually still under review, so if there are any reviewers, just be gentle with the review because it is a very nice paper. Okay, so this is the essence of the methodology. Okay, so I have just a few more slides of examples, and for the sake of simplifying the life of my chairperson, I would like to stop it here because the key message has been already conveyed, I think, and I would be more than willing to answer any questions during the discussion phase that you might have. Thank you very much.
Okay. All right. Well, good afternoon, everybody. I guess it's 12:30. And Before I get started, I'd just like to thank the organisers for the invitation to come here and present some of this work to you all. I actually moved my research group recently to Colorado State University, which is why it says on some of your documents Ohio State, and on here Colorado State. If you need to get in touch with me, that's my new email address there. And so it's probably a case of something a little bit different now. We're going to talk about the microbiology of these shale systems. And so this is something that we've been working on with sort of a US-centric focus, obviously being at Ohio State and at Colorado State, for the last couple of years. But before we dive into to the data, I just want to acknowledge the people that have worked on this project. So there's a whole series of collaborators at Colorado State University, at Ohio State, at New Hampshire, and some Department of Energy user resources. Graduate students who did a lot of the work I'm going to show today, and then also various types of support from the National Science Foundation, from Nettle, and then also we just heard about the Deep Carbon Observatory. They provided various kinds of support as well. So we'll start off with just a map of shale plays across the US. For a lot of this work, I was based in central Ohio, and so a lot of the work has been focused in the Appalachian Basin, in the Marcellus and the Utica shales. We've more recently moved down into a number of shale plays down in Texas, up into the Stack Formation in Oklahoma, and then the DJ Basin in eastern Colorado as well. But most of the work will be focused on processes that we've inferred occurring in the Appalachian Basin. So the key point I want to make, first of all, with regards to the microbiology, is that prior to hydraulic fracturing, so shales in their natural state, particularly in the Appalachian Basin, are pristine with regards to microbial life. And hopefully this shouldn't be too surprising based on a number of the talks that we've seen already today. We spent a number of years looking for microbial life in these systems. A lot of blood, sweat, and tears went into these studies, and the resulting conclusion was that there is no microbial life. And again, if we think about the levels of porosity and permeability, that's maybe not surprising. Okay, we have nanometer-sized pores. When we think about bacteria or archaea, we're talking on the orders of microns. So there simply isn't the habitat for these microbes to live in the vast majority of normal unfractured shales. Of course, when we frack these systems, we inject huge volumes of water, some chemical additives and proppant into these systems and generate these fracture networks. Because of the sheer volume of fluid that goes into these systems, it's basically impossible to keep that material sterile. And so as we hydraulically fracture these shale formations, we inadvertently introduce microorganisms into the system. So these are microbes that are present in storage tanks on the surface. They may be present on the surface of proppant material. Irregardless, they make their way down into the deep subsurface and find these beautiful new fracture networks that have just been generated. And they're able to colonize these systems. What we've been able to do across the Marcellus and the Utica down into the Permian Basin is work with operators, a range of operators, and actually collect fluids at the wellhead. So as that water and the hydrocarbons are pumped back to the surface, we're able to take samples and we're able to characterize that for geochemistry and also a range of microbiology. We use a range of microbial molecular tools to investigate who's there in the subsurface and what are they potentially doing in these systems. So the first takeaway point for you today is that we see, again, with the caveat, this is mainly in the Appalachian Basin, but it is sort of expanding into other systems, we see a lot of the same microorganisms. We see this conserved microbial community that are present across a whole series of different shale wells. So here you can see this concentration of Appalachian Basin wells up into the Antrim Shale up there in Michigan, and then down into Texas here. And what I'm showing here is that we see the same group of 5, 6, 7 microorganisms in all of these systems. And so perhaps the best example, which I'll focus on a little bit later, is this microorganism that we call halanaerobium. Okay? This completely red circle tells you that this is present in every single well that we've looked at. Okay? So it's extremely conserved across these systems, and in many cases it's the dominant microorganism. So if we look at the whole community, this is the dominant microbe that's present in these systems. The other bug here that I want to draw your attention to is Methanahalophilus, okay? And you can probably infer a few things from these names. Halophilus, this is salt-loving, but also methano, or right? This is actually a member of the archaea that produces methane in situ, so new sources of biogenic methane. And again, this is a very common microorganism that we see in many of these shale wells. Now, the question is, why do we see this extremely conserved population? For example, if you look in surface soils and agricultural soils, you'll have thousands of different kinds of microorganisms. And yet, in shales, we see 5, 6, 7 types of microbe. And we think this is linked to the extreme salinity that you observe in these systems. And so here we're using conductivity as a proxy for salinity, and then we're looking at the number of days after hydraulic fracturing. So each one of these lines is an individual well, either in the Utica Shale, the Marcellus Shale, the Wolfcamp down in Texas, and then the Stack Formation over in Oklahoma. And so, particularly in the Marcellus and the Utica Shale, you can see that we initially put fresh water into these systems. That fresh water reacts with these old marine rocks. And so you see this very rapid increase in salinity as we get salt moving into the aqueous phase. And I've put on a couple of things here, seawater and the salinity of the Great Salt Lake, just as context for how saline these fluids are. They're extremely salty. The same goes for the Wolfcamp, and to a lesser extent, as we move into some of these new shale plays in Oklahoma, we see much lower salinity in these systems. But particularly in the Appalachian Basin, we have brine-level salinities that these microbes have to persist in. These are very extreme conditions, and so only very specialized microbes can live in those kinds of environments. So what's a problem with salinity like this? Unfortunately, the best diagrams for these kind of concepts are always shown with red blood cells, but the concept's the same for microorganisms. You'll just have to bear with me. But this is the situation. If you're a microorganism in that kind of salinity that we might find in the Utica or the Marcellus Shale, what happens? Water inside the cell leaves the cell. It tries to equilibrate with that extracellular environment. So your cell shrivels up and your cell dies. Okay? So how do microbes survive in a system with sort of those brine-level salinities that we see in the Marcellus Shale? Well, there's a couple of strategies, but there's one I want to highlight here. They produce compounds that go via a range of names. I may call them osmoprotectants. I might call them compatible solutes. These are organic molecules that cells produce or uptake from the environment, and they help to stabilize the internal structure of the cell so that they can survive in these extremely saline conditions. And so that's all you're seeing in this diagram here. This cell is taking up this compound, and a great example of a compatible solute, of an osmoprotectant, is glycine betaine, okay? And that's the structure of that compound there. All right, so this is going to be important for the next couple of slides. So cells in this system use glycine betaine to protect themselves against this salinity stress. So how do these communities, this 5, 6, 7 different microorganisms, how do they persist thousands of meters underground? Hot conditions, high salinity, high pressure. So this is what we've inferred based off of sort of the range of the microbiological analyses that we've done. So again, we have our microbe here. It might be producing glycine betaine in the cell. It might be taking it up from the external environment. One thing I haven't told you so far is that in addition to microbes in these systems, there are also lots of viruses. We see huge abundances of viruses in these deep shales. And these are viruses not of humans, but of bacteria and archaea. This is just an image here, and you can see, well, maybe you can't, this scale bar down here is 50 nanometers. So these viruses of bacteria are extremely small. What they'll do is they will attach on to the outside of these microbial cells, and they will try to infect these microbial cells. And whereas if we get a virus, we get sick for a few days, and then hopefully we recover, if you're a bacteria and you get infected by a virus, it's far more terminal. Eventually what happens is the viruses reproduce inside the cell, and they burst the cell open, releasing more viruses, but also releasing compounds such as glycine betaine. And so here is a transmission electron micrograph showing one of these cells being burst open, and then all these viruses and intracellular compounds being released into the external environment. The last step of this process is that these sort of tasty organic compounds, this glycine betaine, can be used by other community members. And so eventually what happens is we have fermentation reactions of these compounds that produce substrates for methanogenesis. And the critical point I want you to take away here is this is not sort of the classical methanogenesis that you might be familiar with, okay? If you're familiar with methanogenesis, you assume it comes from acetate or from hydrogen and CO2. This is a different kind of methanogenesis that we see in this system. This is a methanogenesis from methyl compounds. And so you can see these methyl groups are eventually converted into methane. And so it's basically this very simple system of bacteria, archaea, and viruses that helps the community to persist in these shales for extended periods of time, hundreds of days. So at this stage, the question is, well, that's sort of an overview about how we infer these communities to persist, but what are the implications for reservoir performance? And so I'm going to focus, sort of however long I have left, on halanaerobium, that microbe which we see in every single well, and what the implications of halanaerobium growth might be like in this system. And of course, we're interested in this for a number of reasons. Obviously, microbes can form biofilms and clog those pores and fractures, which operators have spent a lot of money generating in the system. They can also drive extensive corrosion of subsurface infrastructure. And then they can also produce sulfide, which of course is a toxic product, so rig workers are at risk of sulfide, but it can also drive the precipitation of minerals as well and cause further clogging. All right, so microbial activity is generally considered pretty deleterious in these systems. So first of all, let's look at sulfide production. And so this is halanaerobium. And what you're looking at here is the density of cells across by time, and then also sulfide being produced. And if you talk to the majority of operators, both in conventional and unconventional reservoirs, they're concerned about sulfide being produced from the reduction of sulfate. Okay? That's the major concern, especially in offshore reservoirs. What we've shown here, especially in the Appalachian Basin, is that sulfate reduction doesn't happen. Instead, sulfide is being produced from thiosulfate. And so what we're looking at here is halanaerobium growing with and without thiosulfate, and we don't see very much difference in terms of the amount of cells that are produced, but we do see millimolar quantities of sulfide being produced. So pretty large volumes of sulfide, and it's coming from thiosulfate rather than sulfate. This, of course, sort of poses a series of questions. The first of all is, where might thiosulfate come from? And if we look at some frac chemistries, thiosulfate is often injected into the subsurface as an additive. And of course, if that's then driving sulfide production, that's not a good thing. The other possible source is from shale rock itself. We've done some very sort of basic preliminary work looking at the leaching of compounds out of the shale matrix if it's put into contact with fresh water. And sure enough, you see thiosulfate coming out of that shale rock. The other implication is that a lot of industry tests for sulfide production focus on sulfate-reducing bacteria using what are called bug bottles, basically enrichments for sulfate-reducing bugs. Of course, these enrichments completely miss thiosulfate-reducing microbes. And so if you use some of these traditional tests, you won't accurately know the extent of sulfide production in your system. So that's the first possible impact of microbial growth. The second one I'd like to draw this, I guess I'll just show you some pretty pictures before I get ahead of myself. These are some very simple sort of bioreactors we set up where we incubated steel coupons in the presence of different chemistries. And so first of all, we have our control. So here's a well-known sulfate-reducing microorganism growing in media with sulfate, and you can see that characteristic black sulfide precipitate. We also have our negative controls here. So these are frac fluids amended with sulfate and frac fluids with no addition. And you'll see we don't see any sulfide production here. There's none of that black precipitate. And yet, here we have our bug, halanaerobium. We add some thiosulfate. You can see sulfide being produced. And then if we simply amend our frac fluids with thiosulfate, that reduction happens. So the natural microbial community in the frac fluids reduces the thiosulfate to sulfide, and you can see again the black sulfide precipitate. If we just zoom in more closely to our positive, our halanaerobium and thiosulfate, and look at the actual steel coupon in there, you can see degradation on that steel surface. We've got precipitated sulfides and potentially some corrosion going on under there as well, okay? So again, just to re-emphasize, we don't want microbes producing sulfide in this system. It doesn't do anything good to the system. The other thing to consider when we talk about the microbes is that, remember, these are seeded from the surface, okay? The bugs are originally present in surface input fluids. Suddenly they find themselves kilometers underground in very salty conditions, very hot conditions, but also under high pressure conditions as well. And so one question was, well, how do these microbes respond to these high pressure environments? And so the first experiment we did was to take a halanaerobium bug that we isolated from the shale, and grow it under a whole series of pressures. So atmospheric pressure, 3,000, 5,000, and 7,000 psi. So pressures characteristic of the deep subsurface to see how fast it grew. And that basically there is this scale in red. So if you look at the red bar, first of all, the takeaway is that the microbe really prefers to grow at atmospheric pressure. But if you incubate it at pressure, it will still grow, okay? And so we can characterize this bug as what we call piezo-tolerant, so pressure tolerant rather than piezophilic, pressure loving, okay? So this is a pressure tolerant bug, so it will still grow, not unsurprisingly, in these subsurface pressures. We were interested in how the microbe was actually doing this growth, how it's performing this growth, and so we used a technique that allows us to analyze all the proteins that a microbe is producing under a given condition. For example, at 3,000 or 5,000 psi, which proteins is it producing? And so we call this is what's called comparative proteomics. It doesn't really matter, but here you can see these pressures, and the color scheme just refers to the abundance of these proteins. And so don't pay any attention to the names of the different proteins here, but hopefully you can see a clear pattern that the proteins at atmospheric pressure are all relatively low abundance, and these proteins here are all relatively high abundance under pressure. Okay? Hopefully that's clear from that heat map. The takeaway point here is that as the pressure increases, all these proteins are involved with what we call slime production, okay? Or more specifically, extracellular polymeric substances, but we'll call it slime for the purposes of the rest of this talk. So the bugs, under pressure, are producing more slime. What does that mean? This, again, is just a bar chart, just sort of showing this is statistical. This has a statistical basis. We see more of this EPS production under pressure. And this is an image at 14 psi, and hopefully you can see better back there than I can down here. But what we've done is we've stained the cells red, and we've stained that slime green, and we've looked at it under a microscope. And so you can see the cells, hopefully, these red specks on this image here, and there's very little EPS there. There's very little of this slime being produced at atmospheric pressure. We can contrast this with high-pressure incubations, and perhaps this image here is the nicest. You can see this sort of cluster of cells here, and you can see this much greater volume of this slime material. And we can overlay these images and see that under pressure, the cells form these sort of aggregates of biomass and slime. And again, when you think about these sort of very small pores and fractures that are being generated in these shale plays, it wouldn't take too much of this material to start to plug up some of those fractures and pores and potentially contribute to decreases in reservoir performance. Okay, so it looks like my timing's probably good, because I think at this point I just want to leave with a couple of closing thoughts at this stage. The first point is that in every system that we've looked at, and we've looked in, well, 20, 30 wells across multiple shale plays in the US, microbes are present everywhere. It's functionally impossible to sterilize completely the fluids that are going down the hole. It's impossible to sterilize all the equipment, the insides of the frac tanks, the holding tanks. And so you're going to have microbial communities in your system. It's a question of how do you control them. And so one key point is that within these communities, we almost always see methane-generating members. Okay, so archaeal members of these communities that generate methane. So as we see reservoir performance, reservoir efficiency decrease over time, in the future, is there the potential to leverage the presence of these methane-generating bugs? Can we shut these wells in, put some additive downhole, let them generate new quantities of biogenic methane that can then be recovered down the line? The other point is that because we have this relatively conserved community, it means that potentially management strategies, so microbial control strategies, could be designed maybe on a basin scale, maybe more generally, for more efficient microbial control. And then finally, obviously, hopefully I sort of conveyed some of this, especially with haloneurobium, this microbe that we see in all these shale wells. It's frequently a dominant member. I think we can assume this is probably driving deleterious processes in the subsurface, and I just highlighted two of those there. This large-scale production of sulfide from thiosulfate, and also the potential for bioclogging based on the fact this bug produces a lot of slime when it's incubated under relevant in situ conditions. So I'll just leave those up there as I finish. Thank you for your attention, and hopefully I'll take some questions when we're done. Thank you.
Good afternoon. My name is Mike Dinkle. I'm with Anadarko Petroleum. And like Dr. Wilkins, I'm also from Colorado. I'm from just down the road from him. We've worked with CSU in the past on numerous projects. So thank you to the forum for allowing me to fly over here and check out this great country. We did come a little early and stayed with a buddy down in Brighton who's from London, and everything is bloody this, bloody that, dolling pedal, so if I accidentally drop a bollocks or something, I apologize. I work in primarily 3 basins. I work in the Powder River Basin in Wyoming, which is in the appraisal mode, maybe 8 wells drilled, 10 more planned next year. So it's a very different basin than the others. Water's trucked in. They use EVAP pits for water disposal. I also work in the Permian Basin in West Texas. That's in that we've passed the appraisal mode.